Look up at the night sky on a clear evening, and what do you see? Pinpricks of light scattered across a seemingly endless darkness. But what if I told you that this darkness isn't empty at all? That between those distant galaxies lies something far more mysterious and profound than the stars themselves. An invisible ocean of matter and energy so vast it defies comprehension. This is the intergalactic medium, the universe's greatest unsolved puzzle, a hidden dimension of reality that holds secrets about everything from the birth of galaxies to the ultimate fate of the cosmos. Imagine for a moment floating in that profound silence between galaxies. You are surrounded not by emptiness, but by a thin, electrified mist, a cosmic web of gas and dark matter, threads of creation stretching across billions of light years. This isn't science fiction, it's the fabric of our universe, and it's teeming with questions we've only just begun to ask. How did this vast structure form? What strange forces are at work within it? And what can it tell us about where we all came from and where we're headed? Throughout human history, we've looked to the stars for answers, but some of the universe's most profound mysteries aren't in the light, they're hidden in the shadows. In this journey, we'll explore 30 of the most captivating enigmas of the intergalactic medium, each one a doorway to understanding the cosmos on a scale that stretches both imagination and science to their limits. This is more than a tour of cosmic curiosities. It's an invitation to wonder, to question, and to feel the awe that comes from confronting the unknown. So let's begin not at the stars, but in the spaces between them, where the real story of the universe is waiting to be discovered. Our journey into the unknown begins with a cosmic case of misplaced matter. For decades, cosmologists have been confronted by a deeply puzzling inventory error. Based on our most robust measurements of the early universe, primarily from the cosmic microwave background, we can calculate with incredible precision how much normal matter, the protons and neutrons that make up everything we can see, from stars to planets to you and me, should exist today. This matter is known as baryonic matter. Yet, when astronomers add up all the ordinary matter they can actually observe in the present-day universe, all the stars, all the glowing gas in galaxies, all the dust, they come up dramatically short. The numbers just don't match. We're talking about a staggering deficit. Over half of all the normal matter in the universe is simply unaccounted for. This isn't a small rounding error. It's the missing baryons problem, and for a long time it represented a profound embarrassment for astronomy. How could we possibly lose track of something as fundamental as the building blocks of the cosmos itself? The search for this missing matter has taken scientists on a galactic scavenger hunt. They've looked everywhere imaginable. Could it be locked inside faint, undetected stars? The surveys say no. Perhaps it's concealed within massive black holes. The math doesn't support it. Maybe it's in the form of cold, dark clouds of gas drifting unseen within galaxies. Extensive searches have turned up only a fraction of what's needed. Each time a new hiding place was proposed, observations would eventually rule it out, deepening the mystery. It seemed as if the universe was playing an elaborate game of hide and seek with its own ingredients. The prime suspect, the most logical hiding place for such a vast amount of material, is the very space we thought was empty. The immense voids between galaxies are not truly void at all. Theorists now believe this missing matter is spread throughout the intergalactic medium, woven into the cosmic web. But it's not in a form that's easy to see. This matter isn't gathered into bright, shining stars. It's believed to be an incredibly hot, incredibly thin soup of ionized gas, so diffuse that it's virtually transparent. This gas is heated to temperatures of millions of degrees, making it emit light not in the visible spectrum, but in far more energetic X-rays. Detecting this faint, high-energy whisper against the backdrop of the universe is one of the greatest technical challenges in modern astrophysics. Finding this missing matter isn't just about balancing a cosmic ledger. It's about confirming our fundamental understanding of the universe's structure and history from its first moments to the present day. So if the missing matter isn't hiding in plain sight, where could it possibly be? The leading theory points us toward a ghostly component of the cosmic web known as the Warm-Hot Intergalactic Medium, or WHIM. Picture this not as a cold, dark fog, but as a searing, invisible plasma. This is gas that has been superheated to astonishing temperatures, ranging from 100,000 to 10 million degrees Kelvin. At these extremes, the atoms are torn apart, stripped of their electrons, becoming a thin soup of ions that simply doesn't glow in a way our telescopes can easily see. It's like trying to spot the heat haze rising from a desert highway from 1,000 miles away. The signal is faint, distorted, and incredibly challenging to isolate from the background. The primary method for hunting this elusive matter relies on a cosmic trick of the light, using the brightest beacons in the universe, quasars. These are the immensely powerful cores of distant galaxies, shining with the intensity of 1 trillion stars. As their light journeys across billions of light years to reach us, it passes through these vast filaments of hot gas. The WHIM doesn't emit much light, but it does absorb very specific wavelengths. Scientists meticulously analyze the quasar's spectrum, the breakdown of its light, into a rainbow of colors, searching for telltale, dark lines. These lines are like cosmic barcodes, each one indicating the presence of a specific element, like oxygen or neon, that has absorbed the quasar's light. Finding these faint absorption lines is the key evidence that the WHIM is there, its presence recorded in the light that managed to pass through it. Another ingenious technique involves observing the cosmic microwave background, the faint afterglow of the Big Bang. As this ancient light travels through the universe, it occasionally passes through massive galaxy clusters. If those clusters are surrounded by the hot electrons of the WHIM, those electrons interact with the CMB photons in a subtle but measurable way, imparting a tiny amount of energy to them through a process known as the Sunyaev-Zeldovich effect. This interaction creates a specific distortion in the CMB's signature, a faint shadow that, when mapped, can theoretically reveal the distribution of this hot gas. It's an incredibly subtle measurement, like trying to detect the minute wake left by a fish deep below the surface of a vast, choppy ocean. Confirming the existence of the WHIM is about far more than just solving an accounting problem. It would validate our most fundamental models of cosmic structure formation. According to these models, the gravitational pull of dark matter drew normal matter into vast filaments, and as gas fell into these cosmic highways, it was shock-heated to these tremendous temperatures. Finding the WHIM is the crucial final piece of evidence that our story of how the universe built its large-scale architecture is correct. It's the difference between having a theory and having proof written in the superheated fabric of space itself. But if the WHIM is the superheated gas filling the cosmic plumbing, what exactly is the plumbing itself made of? This brings us to the grand, invisible architecture that underpins the entire universe, the cosmic web. To truly grasp the structure of the intergalactic medium, we must first understand that it is merely the visible tracer, the luminous paint, brushed onto a scaffolding built from something we cannot see at all. The blueprint for the entire universe is drawn in dark matter. The story of this cosmic architecture begins in the faintest whispers of the Big Bang. Tiny, random fluctuations in the density of the primordial universe were imprinted on the fabric of space-time itself. These minuscule wrinkles in reality were the seeds of everything to come. Over billions of years, the relentless force of gravity acted on these seeds. But here's the crucial part: ordinary matter, the stuff that makes up planets and people, was too weak to start the process on its own. It was the gravitational pull of dark matter, this mysterious, invisible substance that does not interact with light, that provided Chinese letter. Think of dark matter as the universe's unseen foreman and construction crew, while ordinary matter is just the building supplies waiting to be assembled. As gravity worked its magic, this dark matter collapsed first, flowing into the densest regions of those ancient fluctuations. It didn't collapse into neat spheres, but into an intricate, interconnected network of dense knots connected by long, thin threads with enormous, empty voids in between. This is the cosmic web, a vast, three-dimensional skeleton on a scale that is almost impossible to mentally visualize. The nodes of this web are the future homes of massive galaxy clusters, the bustling metropolises of the cosmos. The filaments are the great cosmic highways connecting them, and the ordinary matter, the baryons, had no choice but to follow. Drawn by gravity, gas flowed along these dark matter filaments, funneling toward the nodes, heating up as it went and eventually cooling to form the galaxies we see today. The profound mystery here is that we are living in a universe whose primary structure is made of a material we cannot directly detect. We are like spiders sensing the vibrations along a web we are blind to. We know the web is there because we can see how it orchestrates the motion of the galaxies. Galaxies aren't scattered randomly, they are aligned along these invisible filaments, streaming toward the massive clusters at the intersections. It's the gravitational influence of the unseen dark matter that guides this cosmic dance. So how do we map something that is, by its very nature, invisible? Astronomers have become cosmic cartographers of the unseen, relying on two powerful, indirect techniques. The first is through immense galaxy surveys. Projects like the Sloan Digital Sky Survey have meticulously mapped the three-dimensional positions of millions of galaxies. Because galaxies trace out the underlying distribution of dark matter, much like lights outlining a city on a nighttime map from space, these surveys allow us to infer the web's structure. By plotting the locations of these galaxies, we can statistically reconstruct the ghostly architecture between them, revealing the filaments and voids in stunning detail. The second tool is computer simulation. With some of the world's most powerful supercomputers, cosmologists run what are called n-body simulations. They start with the initial conditions of the early universe and then let the laws of physics, primarily gravity, play out over billions of virtual years. The results are breathtakingly detailed digital universes that predict how dark matter should clump and form filaments. When we compare these simulated universes to our real maps of galaxies, the agreement is remarkable. It's a powerful validation of our models, suggesting we are on the right track to understanding this hidden framework. These simulations don't just show a static picture, they show the cosmic web as a dynamic, evolving entity, with matter constantly flowing along its filaments, feeding the growth of galaxies and clusters in an endless cycle of construction. Picking up from that grand cosmic architecture, we arrive at a pivotal moment in our universe's history, a profound transition that shaped the nature of everything we see today. To understand it, we have to journey back to a time before stars and galaxies, to an era when the entire cosmos was a much simpler and much darker place. Immediately following the Big Bang, the universe was a searingly hot, dense plasma of particles and energy. As it expanded and cooled about 380,000 years later, electrons and protons finally combined to form neutral hydrogen atoms. This event, known as recombination, cleared the cosmic fog. For the first time, light could travel freely, and we see the afterglow of that moment today as the cosmic microwave background. But this clarity came with a catch. The universe was now filled with this neutral hydrogen gas, and for hundreds of millions of years, it was a profoundly dark and quiet place. This period is rightly called the Cosmic Dark Ages. The darkness wouldn't last. Eventually, the first stars and galaxies began to ignite within the densest knots of the dark matter web. These weren't just any stars, they were behemoths, monsters known as population 3 stars, thought to be hundreds of times more massive than our sun and burning ferociously hot and bright. Their birth marked the beginning of the cosmic dawn, and they brought with them a force that would utterly transform the universe: intense ultraviolet radiation. This high-energy light from the first stars and the voracious black holes in the first quasars began to rip electrons away from the neutral hydrogen atoms that filled all of space. This process of turning neutral atoms back into a plasma of free electrons and protons is called ionization. The era when this happened across the entire universe is known as the epoch of reionization. It was a fundamental phase change for the intergalactic medium, a second great clearing that made the universe transparent to the specific types of light we use to observe it today. Think of it like a cosmic scale sunrise. Before reionization, if you could somehow be there, any distant source of light would be shrouded and blurred by the pervasive neutral hydrogen fog. This gas absorbs the very specific ultraviolet light known as Lyman-alpha radiation. After reionization, that fog is burned away, and the light from distant galaxies can travel across the universe almost unimpeded, straight into the lenses of our telescopes. This is why we can see so far back in time. Reionization is the event that lifted the final veil, but the details of this epoch are shrouded in mystery. We know it must have occurred, but the how, the when, and the who responsible are some of the most active and contentious areas of research in all of cosmology. Pinpointing the exact timeline is incredibly difficult. The best evidence we have suggests that reionization was not a swift, singular event but a drawn-out process that began around 500 million years after the Big Bang and was mostly complete by around 1 billion years. However, this is a broad window, and refining it is a major goal. The key to studying this is to look for the very first objects that ended the Dark Ages. The Hubble Space Telescope has pushed our view to incredible distances, spotting faint galaxies from when the universe was less than 500 million years old. The new James Webb Space Telescope is now going even further, peering into that crucial era, searching for the earliest, faintest glimmers that began this great transformation. By counting these galaxies and measuring their brightness, we can try to determine if there were enough of them to produce the radiation needed to reionize the entire cosmos. This leads directly to the hot debate. What were the primary engines of reionization? Was it the collective effort of countless small, faint early galaxies? Or was it driven by a smaller number of tremendously powerful and brilliant quasars? The answer likely lies somewhere in between, but each possibility paints a very different picture of the early universe. If small galaxies did the bulk of the work, it tells us that star formation was efficient and widespread very early on. If quasars were the main drivers, it suggests that supermassive black holes grew to enormous sizes astonishingly quickly, a challenge to our current models. The truth is, we still don't have a complete census of the objects that existed at that time, which is why the data from new telescopes is so revolutionary. Another layer of mystery involves the mechanics of the process itself. Reionization didn't happen uniformly like a rising tide smoothly covering a beach. Instead, it was likely patchy and bubbly. Imagine the first stars turning on in isolated pockets. Each of these early sources would have created a growing bubble of ionized hydrogen around itself. Over time, these bubbles expanded and overlapped, eventually merging to fill the entire universe with ionized plasma. Mapping the size and distribution of these bubbles is a key to understanding the properties of the first sources of light. This patchiness should, in theory, leave a faint imprint on the way light from the cosmic microwave background is polarized, and experiments are actively searching for this signal. The significance of solving the reionization mystery cannot be overstated. It is the final major phase transition in the history of the universe, and it directly connects the simple plasma of the Big Bang to the complex, structured cosmos we inhabit. Understanding it is essential to interpreting almost every observation we make of the distant universe. The light from the earliest galaxies is modified by its journey through the final remnants of this process. By unraveling reionization, we are essentially reading the biography of the first stars and galaxies, learning how they lived, how they died, and how they collectively changed the nature of reality itself, lighting up the cosmos for all that was to come. Now, if the epoch of reionization was the great event that burned away the neutral hydrogen fog, then the Lyman-alpha forest is the ghostly echo of that process, a permanent record of the few stubborn clouds that were left behind. To find it, astronomers once again turn to the universe's most brilliant lighthouses, quasars. When we point our most powerful spectrographs at a quasar, we don't just see a clean, smooth rainbow of light. Instead, we find something astonishing. The spectrum is absolutely filled with hundreds, sometimes thousands, of sharp, dark lines crowding together, a dense thicket of missing light that astronomers poetically call the Lyman-alpha forest. Each one of these lines is a tiny piece of the story of the intergalactic medium. The science behind this is both elegant and powerful. Neutral hydrogen gas has a very specific appetite. It loves to absorb light at one particular wavelength in the ultraviolet part of the spectrum, known as the Lyman-alpha line. Now, imagine the light from a distant quasar traveling across billions of light years to reach us. Along its immense journey, it passes through countless clouds and filaments of neutral hydrogen gas that are still drifting in the vast intergalactic spaces. Each time the light passes through one of these clouds, the gas acts like a filter, absorbing a tiny bit of light at that specific Lyman-alpha wavelength. But here's the crucial part, because the universe is expanding, each cloud is moving away from us at a different speed due to the Hubble flow. This motion stretches the wavelength of the absorbed light, a phenomenon known as redshift. A cloud that's farther away is moving faster, so its absorption line is shifted farther toward the red end of the spectrum. A closer cloud has a smaller redshift. The result is that a single, specific absorption wavelength gets smeared out across the spectrum, creating a whole forest of lines. Each line corresponds to a different cloud at a different distance along the line of sight. It's as if we've been given a core sample of the universe, a biopsy needle that has pierced through cosmic history, with each absorption line representing a different layer of time and space. This transforms a quasar's spectrum from a simple beam of light into one of the most powerful diagnostic tools in all of cosmology. By analyzing the spacing, the depth, and the width of these thousands of lines, scientists can reconstruct the physical conditions of the intergalactic medium across eons. The density of the lines tells us how much neutral hydrogen is present at different epochs. The width of a line can reveal the temperature and pressure of the gas cloud that created it. It's like taking the temperature and measuring the density of the universe at thousands of different points in its history, all from a single observation. This data has been instrumental in mapping the large-scale structure of the cosmos, confirming the existence of the cosmic web's filaments, and understanding how the universe became transparent after the Dark Ages. Yet, for all its utility, the Lyman-alpha forest is born from a deep and persistent mystery. The precise physical mechanisms that create the intricate structure of these clouds, their sizes, their distribution, their sheer number, are not fully understood. We see the patterns, but the exact processes that paint them remain elusive. Why is the gas clumped in this particular way? What are the detailed effects of gravity, dark matter, and the intense background radiation from galaxies constantly working on this diffuse material? The forest is not a static entity, it's a dynamic, evolving record of constant interplay. Gas is continuously flowing along the cosmic web, falling into galaxies, being blown out by galactic winds, and heated by shock waves from colliding structures. All of this violence and motion leaves its mark on the absorption lines, creating a complex pattern that is incredibly difficult to decode completely. The greatest challenge lies in the fact that these clouds are not simple, isolated spheres. They are likely sheet-like structures or long, thin filaments, and the light from the quasar might be cutting through them at different angles, giving us a distorted view of their true shape. Furthermore, the gas is not just sitting still, it's turbulent. This internal motion broadens the absorption lines, making it hard to disentangle the effects of temperature from the effects of turbulence. Sophisticated computer simulations try to replicate the forest by modeling the growth of structure in the universe. And while they can produce a believable-looking forest, the devil is in the details. The simulated forests often don't match the observed ones perfectly, particularly when it comes to the number of very narrow lines or the properties of the broader ones. These discrepancies are the clues. They tell us that our models of feedback, how energy from stars and black holes is injected back into the intergalactic medium, are still incomplete. They hint at unknown physical processes, perhaps even the subtle effects of warm dark matter or other phenomena we have yet to even consider. The Lyman-alpha forest is therefore much more than a handy tool. It is a profound cosmic mystery in its own right, a natural laboratory written in light that allows us to stress test our understanding of physics on the very largest scales. But the story of the intergalactic medium is not just about the structure of space or the history of light. It's also a story of cosmic contamination. If you were to take a sample of that incredibly thin gas between the galaxies and run it through a cosmic spectroscope, you would make a startling discovery. It isn't pristine. Mixed in with the hydrogen and helium from the Big Bang are trace amounts of heavier elements, carbon, nitrogen, and most puzzling of all, oxygen. We call these elements metals in astronomy, and their presence in the middle of nowhere is a profound mystery. This is the intergalactic medium's oxygen problem, and it points to a universe that has been thoroughly and violently polluted. Finding oxygen billions of light years from the nearest galaxy is like finding a bottle floating in the middle of the ocean with a label from a country that doesn't exist anymore. It's evidence of a dramatic event, a message from a long-forgotten catastrophe. These heavy elements are not forged in the quiet emptiness of space. They are born in the nuclear furnaces of stars and in the spectacular violence of their deaths. Every atom of oxygen in your body was once inside a star that lived and died long before our sun was born. For these elements to end up so far from home, they must have been violently ejected from their host galaxies and hurled deep into the cosmic voids. The sheer scale of this distribution is what boggles the mind. We aren't talking about material being blown just to the outskirts of a galaxy. We are talking about winds and explosions so powerful they can seed intergalactic space with their debris across millions of light years. So what cosmic forces could possibly be responsible for this immense clean-up job? Astronomers have two primary suspects, both of them titanic in their power. The first is the collective effect of supernova winds. In a starburst galaxy where stars are forming at a ferocious rate, massive stars live fast and die young, exploding as supernova in quick succession. Individually, a supernova is a tremendous explosion, but when they occur in the thousands or millions, their combined energy can overpower the galaxy's gravity. This creates a gigantic outflow, a super wind that blows the enriched contents of the galaxy's core, the oxygen, silicon, and iron created in those stars right out of the galaxy entirely, injecting it directly into the intergalactic medium. It's like a volcanic eruption on a galactic scale, spewing ash and gas high into the atmosphere where it can then circulate globally. The second, and perhaps even more powerful suspect, is the active galactic nucleus, and the incredibly energetic core of a galaxy powered by a supermassive black hole. As matter spirals into the black hole, it doesn't go quietly. Intense magnetic fields can funnel some of the infalling material into jets that blast out from the poles at nearly the speed of light. Meanwhile, the accretion disk itself emits so much radiation that it can push surrounding material outward in a tremendous radiative wind. These AGN-driven outflows are among the most energetic events in the universe since the Big Bang. They can launch material not just out of the galaxy, but can accelerate it to speeds so high that it can escape the immense gravitational pull of the entire galaxy cluster, spraying heavy elements far and wide across the cosmic web. Yet, for all the compelling nature of these theories, the exact mechanics remain one of the great unsolved puzzles. The challenge is one of efficiency and scale. Can these galactic winds actually carry enough material to account for the vast quantities of oxygen we detect? And can they carry it far enough? Computer simulations struggle to get it right. Often, the simulated winds either don't push the material far enough, leaving it in a halo around the galaxy, or they blow out too efficiently, completely shutting off star formation in a way that doesn't match what we observe in real galaxies. It seems to require a perfect and poorly understood balance of energy. Too little energy and the metals fall back. Too much energy and you destroy the galaxy's ability to make new stars. Getting just the right amount of force to pollute the entire cosmos without completely sterilizing the galaxy is a fine-tuning problem that current models haven't fully cracked. This intergalactic pollution has completely changed our understanding of the ecosystem of the cosmos. The heavy elements we find out there are not just random junk, they are the prerequisites for life as we know it. Oxygen, carbon, and nitrogen are fundamental building blocks for planets and living organisms. This means that the very materials necessary for life are not confined to galaxies. They are a fundamental ingredient of the universe itself, woven into its fabric. The first galaxies to form may have violently seeded the entire cosmos with the raw materials that would, billions of years later, allow planets like Earth to form and life to emerge. It suggests a universe that is deeply interconnected, where the life cycle of one galaxy can directly impact the potential for life far beyond its boundaries. Solving the mystery of how this pollution spread so far is therefore about more than just accounting for atoms. It's about understanding our own cosmic ancestry, tracing the long and violent journey of the very elements that make us who we are back to their source in those first frantic eruptions of galactic energy. But for all the talk of the universe being filled with a superheated plasma, there remains a class of enigmatic structures that defy this simple, scorching narrative. Scattered throughout the intergalactic medium, astronomers have stumbled upon something that, by all rights, shouldn't be there: compact, relatively cool clouds of hydrogen gas. In the multimillion-degree furnace of the WHIM, these pockets of gas at a mere 10,000 degrees Kelvin are like finding chunks of ice floating in a volcano. They are the cool CGI clouds, and their very existence is a deep and persistent puzzle, challenging our most basic assumptions about stability and survival in the most hostile of environments. The mystery lies in their precarious position. According to standard physics, a small, cool cloud adrift in a much hotter, thinner medium is in a terribly unstable situation. The immense pressure from the surrounding hot gas should act like a vise, quickly crushing these clouds or causing them to evaporate, dissipating their material into the surrounding void in a cosmically short amount of time. It's a process known as conduction and evaporation, and it should erase these delicate structures on a timescale far shorter than the age of the universe. The fact that we see them at all means they are either being constantly replenished, which seems unlikely given their isolation, or they are being held together and protected by some physical mechanism we have yet to fully understand. It's as if we found a delicate soap bubble that has somehow remained perfectly intact in the middle of a hurricane. So what could possibly be shielding these fragile structures? One compelling theory points to the invisible hand of magnetic fields. The intergalactic medium isn't just a soup of particles, it's also threaded with vast, weak magnetic fields, relics from the earliest moments of the universe or seeded by outflows from galaxies. These magnetic fields, if they are woven through one of these cool clouds, could provide a crucial supporting structure. The field lines could act like a cage, a magnetic bottle that contains the cloud's gas, providing pressure from within that counteracts the crushing force of the external hot gas. This magnetic armor could significantly slow down the process of evaporation, granting these clouds the longevity we observe. Another possibility involves the internal dynamics of the clouds themselves. Perhaps they are not static blobs, but are constantly being replenished by subtle flows of cool gas along the cosmic web's faintest filaments, a slow and steady drip feed that replaces any material that is lost. Or maybe their stability is linked to turbulence within the cloud, a churning motion that constantly stirs the gas and prevents it from settling into a state where it can be easily destroyed by its surroundings. Discovering and studying these clouds is a feat of observational ingenuity. They are far too faint to see directly. Instead, astronomers once again rely on their cosmic lighthouses, quasars. As the brilliant light of a distant quasar journeys toward Earth, it may pass directly through one of these cool clouds. The neutral hydrogen within the cloud will imprint its signature Lyman-alpha absorption line onto the quasar's spectrum. But because these clouds are compact and relatively dense compared to the diffuse WHIM, they create absorption lines that are distinctly different. They are narrower, sharper, and often have multiple components, hinting at a complex internal structure. By carefully analyzing the precise shape and depth of these lines, scientists can infer the cloud's density, temperature, and even its velocity. In some remarkable cases, if a quasar's light passes behind two different clouds at slightly different distances, we can even get a rough idea of the cloud's size. This painstaking work has revealed that these are not all identical. They come in a family of different types, from the vast Lyman-alpha blobs that can span hundreds of thousands of light years to the more compact and mysterious objects that are the real focus of this enigma. Unraveling the secret of the cool clouds is about more than just understanding a cosmic curiosity. These structures are likely the raw, unused building blocks of galaxies, the leftover fuel that never made it into a star-forming factory. Their survival tells a story about the balance of forces in the intergalactic medium. If magnetic fields are indeed the key to their longevity, then studying these clouds allows us to measure the strength and structure of magnetic fields in the most remote regions of the universe, a measurement that is incredibly difficult to make by any other means. Furthermore, their existence challenges the models of feedback, the very process that spreads heavy elements. The same galactic winds and AGN outflows that pollute the IGM are also incredibly violent. How do these delicate clouds manage to persist in the wake of such enormous energy releases? They represent a delicate and poorly understood part of the cosmic ecosystem, a reminder that even in the vast, violent expanses between galaxies, there can be pockets of unexpected fragility and order, their continued presence quietly testifying to the complex and hidden physics governing the space between the stars. Leaving behind the delicate mystery of the cool clouds, we venture into a far more turbulent and energetic puzzle. The intergalactic medium isn't just a passive backdrop. It's a dynamic and seething environment, a cosmic battlefield where immense forces are constantly at war. And this brings us to a fundamental question that cuts to the very heart of how this vast ocean of gas behaves. What is its temperature? You might assume that such a diffuse medium would have settled into a uniform, lukewarm state, but the reality is a shocking and chaotic patchwork of extremes. Some regions are infernos, blazing at tens of millions of degrees, while other pockets, as we just saw, cling to a relatively frigid 10,000 degrees. This wild inconsistency is the intergalactic medium temperature mystery, and it reveals that our universe is a place of constant, violent, and poorly understood thermodynamic drama. To grasp why this is so puzzling, we need to consider the basic physics of a gas in a vacuum. In a simplified, quiet universe, you would expect the IGM to gradually cool over time as it expands. The initial heat from the Big Bang would slowly dissipate, and the gas would approach a uniform, cold temperature. But the universe is anything but quiet. It is filled with colossal sources of energy that constantly reheat the gas, preventing it from ever settling down. the real mystery isn't that the IGM is hot, it's that its temperature is so uneven and unpredictable. The pattern of hot and cold we observe simply doesn't match the clean, smooth predictions of our most straightforward models. It's as if we expected a gently simmering pot of water, but instead found a pot with violent, isolated geysers next to pockets of ice. So what are the titanic forces capable of reheating this cosmic ocean? Astronomers have identified several prime suspects, each a contender for the universe's most powerful heating system. The first and perhaps most significant is the gravitational heating caused by the formation of the cosmic web itself. As dark matter pulls vast rivers of gas into filaments and knots, the gas doesn't flow smoothly. It crashes into itself, creating immense shock waves, cosmic sonic booms that travel through the intergalactic medium. These shocks violently compress and heat the gas, much like how a bicycle pump gets hot when you compress air inside it rapidly. This process is likely the primary reason for the searing temperatures of the warm-hot intergalactic medium, essentially pressure cooking the gas as it flows into the large-scale structure of the universe. But gravity isn't the only player. The second major source of heat comes from the intense radiation generated by galaxies and their central black holes. As we discussed with reionization, the ultraviolet light from stars is powerful enough to tear atoms apart, and that process doesn't just ionize, it also transfers energy and therefore heat to the gas. Furthermore, the high-energy X-rays and gamma rays from quasars and other active galactic nuclei can penetrate far deeper into the IGM, depositing their energy in remote regions and creating vast, invisible bubbles of superheated plasma. This is radiative heating, a constant cosmic microwave on a galactic scale, and its effects are incredibly complex to map because it depends entirely on the proximity and brightness of these astrophysical engines. However, for all these powerful heating mechanisms, there are equally potent forces working in reverse, trying to cool the gas down. This is where the mystery truly deepens. A primary cooling mechanism is perhaps the most counterintuitive: radiation. When a free electron interacts with a proton in the hot plasma, they can briefly recombine into a hydrogen atom. When this happens, the atom releases a photon of light, carrying energy away from the gas and into space. This process, called radiative cooling, is most efficient in denser regions of gas. It's the universe's natural air conditioning system, but its effectiveness is a double-edged sword. In some areas, efficient cooling allows the gas to condense and eventually form new stars. In others, it might explain how those fragile cool clouds manage to persist. The problem is that the balance between these colossal heating and cooling processes is exquisitely sensitive and wildly variable from one part of the cosmos to another. This is why the observed temperature map of the universe is such a chaotic mess. It's not a simple gradient from hot clusters to cool voids. Instead, we find surprisingly hot gas in what should be quiet regions and unexpectedly cool gas surviving in what should be violent environments. This mismatch is a glaring clue that our understanding of the entire energy budget of the cosmos is incomplete. We are likely underestimating the efficiency of some heating mechanisms while overestimating the power of others. Perhaps the energy from supernova winds is distributed more efficiently through the cosmic web than our models predict. Maybe the magnetic fields that protect cool clouds also play a role in inhibiting heat conduction, preventing hot and cold regions from equalizing and creating a more stable temperature patchwork. Unraveling this thermal mystery requires incredibly subtle and difficult observations. Scientists once again turn to the Lyman-alpha forest for answers. The width of each absorption line in a quasar's spectrum is a direct thermometer for the gas cloud that created it. Broader lines indicate hotter, more turbulent gas, while narrower lines point to cooler, calmer material. By measuring thousands upon thousands of these lines across different redshifts, astronomers can painstakingly reconstruct a rough temperature history of the universe. The results confirm the chaos, They show that the temperature of the IgM rose dramatically during the epoch of reionization, as the first floods of ultraviolet radiation poured energy into the gas, and then began a long and complex journey of heating and cooling that continues to this day, dictated by the ongoing formation of galaxies and the explosive feedback from their stars and black holes. Solving the IgM temperature mystery is therefore about more than just filling in a detail on a cosmic chart. It is central to understanding the cycle of galactic life and death. The temperature of the gas dictates its fate. Hot gas is energetic and resistant to collapsing under gravity, stifling the birth of new stars. Cooler gas can condense, flow into galaxies, and fuel future generations of stars. The patchy and unpredictable temperature of the intergalactic medium acts as a global regulator for star formation across the cosmos. By deciphering why some regions are hot and others are cold, we are ultimately learning what controls the growth of galaxies themselves, uncovering the invisible thermodynamic rules that govern the evolution of everything we see in the night sky. This brings us to a mystery that connects the violent history of the intergalactic medium directly to the very structure of the galaxies we see today. A profound mismatch between prediction and observation that has puzzled astronomers for decades. Our most sophisticated supercomputer simulations of cosmic evolution, which so beautifully recreate the vast cosmic web, present us with a very specific prediction. They tell us that the dark matter halo of a large galaxy like our own Milky Way should be swarming with thousands of smaller satellite galaxies, miniature worlds known as dwarf galaxies. These are the cosmic equivalent of islands surrounding a continent. Yet, when we actually look out into the sky and count them, the numbers are wildly off. We find only a few dozen of these dwarfs, not the thousands we were expecting. This glaring discrepancy is known as the missing dwarf galaxy problem, and for a long time, it seemed like a critical failure of our otherwise successful model of the universe, the lambda cold dark matter model. The simulations are incredibly detailed. They show how small fluctuations in the early universe grow under gravity, with tiny dark matter halos forming first. These small halos then merge to form larger ones in a bottom-up process of structure formation. The result around a large galaxy is a swarm of these small, dark matter clumps, each one massive enough to attract ordinary gas and potentially become a visible dwarf galaxy. So if the dark matter is there, as the simulations insist it must be, why aren't we seeing the galaxies? The answer appears to lie not with the dark matter itself, which is invisible, but with the ordinary matter, the gas that should have turned into stars. And the culprit that prevented that from happening is almost certainly the intergalactic medium, not as a passive backdrop, but as an active, destructive force in the early universe. The leading theory points to a specific and brutal process linked to the epoch of reionization we discussed earlier. Remember the flood of ultraviolet radiation that poured out from the first stars and quasars, ionizing the entire universe. For a large galaxy with a strong gravitational pull, this radiation was a manageable challenge. But for the smallest, most vulnerable proto-galaxies, this cosmic sunrise was an apocalypse. These nascent dwarfs had very shallow gravitational wells, meaning their pull was too weak to hold onto their gas against a strong external force. When the intense UV radiation from the first massive stars hit these small halos, it didn't just ionize the gas, it heated it violently. This process is called photoevaporation. Imagine a blowtorch being held to a ball of ice. The surface doesn't just melt, it violently turns to steam and is blown away. That's what happened to the gas in these small halos. The radiation heated the gas to such extreme temperatures that it achieved escape velocity, boiling off entirely and being blown back out into the intergalactic medium. The dark matter halo was left intact, but it was rendered sterile, a dark, starless ghost, unable to ever form a visible galaxy. This scenario provides an elegant solution to the missing dwarf problem. The simulations are right about the dark matter. There are thousands of small halos surrounding our galaxy. but most of them had their gas stolen from them in that early, violent period, leaving them invisible to our telescopes. This process wasn't random. It had a very specific size limit. Halos above a certain mass threshold had enough gravity to withstand the radiation pressure and hold onto their gas, eventually forming the dwarf galaxies we do see, like the Large and Small Magellanic Clouds. Halos below that critical mass were simply wiped clean. This critical size is known as the filtering mass, and it represents the minimum weight class a galaxy needed to survive the cosmic reionization era. But photoevaporation might not have been the only villain in this story. Another destructive force may have been stellar feedback from within the dwarfs themselves. If a tiny galaxy managed to hold onto its gas long enough to form its first generation of stars, those stars would have immediately become a problem. Massive stars produce powerful winds and then explode as supernova. In a large galaxy, this energy is dissipated, but in a tiny dwarf galaxy with weak gravity, the energy from even a single supernova could be enough to blow all the remaining gas out of the galaxy, permanently shutting down star formation. This self-inflicted wound would leave behind another type of dark halo, one that had a single, brief burst of star formation before being quenched forever. We might be seeing the evidence of this in the ultra-faint dwarf galaxies we have discovered, which contain only a few ancient stars. The search for evidence to support this theory is ongoing and incredibly challenging. How do you find a galaxy that isn't there? Astronomers are looking for the ghosts, those dark matter halos that should host stars but don't. One method is through gravitational lensing, looking for the subtle distortion of light from background galaxies caused by the gravity of these invisible, massive objects. Another is to look for the faintest possible dwarfs, the ones that just barely manage to form a handful of stars. Indeed, recent ultra-deep surveys have discovered a population of these ultra-faint dwarfs, each containing only a few hundred or thousand stars which had previously gone unnoticed. While their numbers are still far short of the thousands predicted, they hint that we are beginning to probe the lower limit of galaxy formation. Each new discovery helps us refine our understanding of that critical filtering mass and the precise timing of reionization's destructive effects. Solving the missing dwarf problem does more than just patch a hole in a simulation. It reveals the IgM as a dominant evolutionary force. It shows us that the early universe wasn't a gentle nursery for galaxies, but a harsh and selective environment. The intergalactic medium, through the radiation that filled it, acted as a cosmic judge, setting the rules for which galaxies were allowed to form and which were doomed to darkness. This process determined the very population of galaxies we see today, shaping the ecosystem of our cosmic neighborhood. It means that the grand narrative of galaxy formation is not written by gravity alone, but by the complex and violent interplay between dark matter, gas, and the searing light of the first stars, a story whose evidence is written in the absence of countless tiny galaxies that never were. While the missing dwarf problem shows us how the intergalactic medium can act as a destructive force, it also hints at another, far more subtle and pervasive mystery woven into the fabric of that very space. We've explored the gas, the heat, and the structure, but there is an even more elusive component at work: magnetism. Scattered throughout the immense voids between galaxies, astronomers have detected the faint but undeniable imprint of magnetic fields. This discovery is as profound as it is baffling because a fundamental question immediately arises: where could these fields possibly have come from? The Big Bang itself is not thought to have produced large-scale magnetic fields, so their presence in the most remote and empty regions of the cosmos represents a deep and enduring enigma, one that forces us to reconsider the energetic history of the entire universe. The sheer scale of these fields is difficult to comprehend. They are not confined to galaxies or even clusters. They appear to be woven through the cosmic web itself, threading through the vast filaments and empty voids that stretch for hundreds of millions of light years. Detecting them is a monumental challenge. Their strength is incredibly weak, 1,000,000 times fainter than Earth's own magnetic field. Scientists use ingenious methods to find them, often by observing the light from distant quasars and radio galaxies. As this light travels through the IGM, the magnetic fields can influence it in two key ways. They can cause a very slight rotation in the plane of the light's polarization, an effect known as Faraday rotation. Alternatively, they can cause electrons to emit a very subtle, diffuse form of synchrotron radiation. Both of these signals are incredibly faint, like trying to hear a whisper in a hurricane, but they provide the crucial evidence that magnetism is a universal phenomenon, a basic ingredient of intergalactic space. This leads to the central puzzle, the origin problem. If these fields weren't born with the universe, how did they get there? The leading theories all point to incredibly dynamic and powerful events in the early cosmos, but each one faces significant challenges. One compelling idea is that they were seeded by the very first stars and galaxies. The turbulent plasmas and powerful winds from supernova and active galactic nuclei could have generated small, localized magnetic fields through dynamo processes. Over billions of years, these galactic winds could have then blown this magnetized material out, polluting the intergalactic medium and stretching these seed fields across colossal distances. It's a compelling idea, like countless tiny sprinklers eventually filling an entire continent with a fine mist. However, the efficiency of this process is hotly debated. Could galactic winds really have distributed magnetic energy so evenly and so thoroughly across the entire observable universe? The simulations struggle to make it work. Another fascinating possibility reaches back to a much earlier time. Perhaps these fields were generated during the extreme violence of the epoch of reionization itself. As the first floods of ultraviolet radiation and plasma from early galaxies expanded into the neutral hydrogen fog, they would have created immense shock waves. These shocks, moving at incredible speeds through the pristine gas, could have generated weak magnetic fields through a process called the Biermann battery effect. This mechanism doesn't require a pre-existing field. It can create one from scratch due to differences in pressure and density in a plasma. If this is true, then intergalactic magnetism was born from the same cosmic dawn that cleared the universe's fog. Yet, even this theory has its gaps, as it's unclear if this process could produce fields on the colossal scales we observe today. A more exotic proposal suggests that these magnetic fields are not astrophysical at all, but are instead a primordial relic generated during a phase transition in the universe's first second of existence, perhaps even during inflation. While the standard Big Bang model doesn't predict this, extensions to the model allow for it. If true, this would mean magnetism is as fundamental to the cosmos as the cosmic microwave background, a basic property of space-time itself. This would be a revolutionary discovery, but currently, there is no conclusive evidence to support it over the astrophysical explanations. The mystery deepens when we consider the field's remarkable coherence. They aren't just random, scrambled patches of magnetism. They appear to be ordered over astonishingly large distances, hinting at a generation and amplification process that is not fully understood. This is where the theory of turbulent dynamos comes in. Once a weak seed field exists, it can be stretched, twisted, and amplified by the turbulent motions of the intergalactic plasma as it flows along the cosmic web. This process could take a faint, primordial whisper of a field and strengthen it into the persistent signal we detect today. But understanding the precise mechanics of this amplification within the diffuse and vast IGM, rather than within a confined star or galaxy, is an immense challenge for theoreticians. Unraveling this mystery is far more than an academic exercise. Intergalactic magnetic fields likely play a crucial, behind-the-scenes role in shaping cosmic evolution. They can influence the propagation of high-energy cosmic rays, guiding these mysterious particles on their journeys across the universe. They may provide the supporting pressure that helps stabilize those fragile, cool clouds of hydrogen against evaporation. They could even affect the growth of structure itself, exerting a tiny but cumulative force on the flow of gas into galaxies. By ignoring these fields, we might be missing a key piece of physics in our simulations of how the cosmos works. Determining their origin and strength is therefore essential to completing our picture of the universe, revealing how the largest structures are interconnected not just by gravity and gas, but by an invisible magnetic force that whispers of the universe's most violent and creative moments. But this grand endeavor to take the universe's measure runs headlong into a profound and humbling reality check. If you were to point a telescope in one direction and analyze the light from a distant quasar, you might construct a very specific picture of the intergalactic medium along that line, the density of the gas, the number of absorption lines, the temperature. Now, if you were to turn your telescope just a few degrees to the side and look at a different quasar, you would likely get a dramatically different answer. This isn't an error in measurement, it's a fundamental feature of our universe. We are faced with the cosmic variance problem, a stark reminder that our view of the cosmos is from a single, fixed seat in a vast and uneven theater, and what we see depends entirely on which way we look. This variance arises from the very nature of the cosmic web. The universe is not a smooth, homogeneous soup. It is a tapestry of dense clusters, long filaments, and enormous voids. When we observe a quasar, its light isn't sampling some universal average. It is taking a single, narrow core sample through this intricate structure. One line of sight might pierce straight through the heart of a massive filament, revealing a dense thicket of absorption lines in the Lyman-alpha forest. Another might pass mostly through a barren cosmic void, showing a spectrum that is almost clean, with only a few isolated lines. We are, in effect, measuring the universe through a drinking straw, and each sip tastes different. This creates a massive sampling error, a cosmic uncertainty principle that challenges our ability to say anything definitive about the true average conditions of the intergalactic medium. It begs the question, how many lines of sight do we need to observe before we can be confident we've seen a fair representation of the whole cosmos? The implications of this problem ripple through all of cosmology, directly impacting our measurement of the most fundamental parameters of reality. Take the determination of the density of ordinary matter in the universe, a number crucial for validating our models of the Big Bang. This measurement is often made by studying the Lyman-alpha forest, as the absorption lines are a direct probe of the amount of neutral hydrogen. But if one quasar's spectrum suggests a high density and another suggests a low one, which one do we trust? Calculating a true average requires a massive statistical sample, observing hundreds or even thousands of quasars to smooth out the wrinkles of cosmic structure. Even then, there's the lingering worry that our corner of the universe might not be entirely typical. We have to assume the Copernican principle, that we do not live in a special place, but cosmic variance is the natural uncertainty that comes with that assumption. This variance also severely complicates our study of the epoch of reionization. The patchy nature of that event means that the size and distribution of the ionized bubbles would have looked dramatically different from various vantage points in the early universe. When we observe the most distant quasars or galaxies, we are looking down specific sightlines that may have been reionized earlier or later than the average. This can skew our estimate of when reionization began and ended, and what primarily caused it. A line of sight that passed through an early bubble near a bright quasar might suggest a very rapid process, while another might suggest a slower, more gradual one. Reconciling these different stories is essential to writing an accurate history of the universe's adolescence. So how do cosmologists combat this inherent fickleness of the cosmos? The answer lies in brute force statistics and ever larger maps. Projects like the Sloan Digital Sky Survey have moved astronomy from the study of individual objects to the science of enormous populations. By meticulously measuring the spectra of hundreds of thousands of quasars, astronomers can finally build a three-dimensional map of the intergalactic medium that is rich enough to average out the variances. They can see not just the individual trees, but the entire forest, its density, and its overall structure. This allows them to measure the true mean density of matter and the true power spectrum of the initial fluctuations from the Big Bang, parameters that are smoothed over the entire observable volume. Yet, in a beautiful twist, the problem itself becomes the solution. While cosmic variance is a nuisance for measuring averages, it is an absolute goldmine for understanding the structure of the universe. The differences between sightlines aren't just noise, they are the signal. The pattern of variations why one region is dense and another is empty holds encoded information about the underlying rules of physics that built the cosmic web. By studying exactly how the properties of the IGM change from one place to another, cosmologists can perform a cosmic tomography, reconstructing the three-dimensional distribution of matter. They can measure the typical size of filaments and voids and test the predictions of their gravitational models against the real, clumpy universe. The variance isn't an error bar to be minimized, it is the data itself, a direct manifestation of the primordial randomness that gravity sculpted into the grand architecture we see today. It teaches us a profound lesson about our place in the universe. We are not merely passive observers of a fixed reality, but active explorers in a vast and varied cosmos where every line of sight tells a different part of the same incredible story. Just as the universe finished its great transition from neutral to ionized hydrogen, another, more subtle but equally profound change was beginning. We've explored the epoch of reionization, when the first stars and galaxies burned away the primordial hydrogen fog. But there was another element present in that early mix, one that would have its own moment of cosmic clarity much later: helium. The story of helium's transformation is a separate and more enigmatic chapter known as the second reionization, or the He-Roman-2 reionization puzzle, and it offers a unique window into a more mature yet still violent universe. After the Big Bang, the universe was about 75% hydrogen and 25% helium by mass. During the initial reionization, the intense UV light from the first objects was powerful enough to strip one electron from each helium atom, turning it from neutral helium into singly ionized helium, known as He-Roman-2. But a helium atom has two electrons, and that second electron is bound much more tightly to the nucleus. To rip it away requires not ultraviolet light, but far more energetic radiation, extreme ultraviolet or even soft X-rays. The first stars and galaxies, for all their power, simply didn't produce enough of this high-energy light to finish the job on a cosmic scale. So for billions of years, the intergalactic medium was filled with this singly ionized helium, a relic of the first reionization, waiting for a more powerful source of energy to arrive. That energy source came with the rise of a specific class of cosmic behemoths, quasars powered by supermassive black holes with exceptionally bright and hard spectra. Around a redshift of 3, or when the universe was roughly 2 billion years old, these objects became numerous and powerful enough to flood the cosmos with the required energetic photons. This event marked the second reionization, the point when the helium in the intergalactic medium finally lost its last electron and became fully ionized He-Roman-3. Unlike the hydrogen reionization, which was a patchy process driven by countless small sources, the helium reionization is thought to have been driven by fewer, much brighter engines, making its history intimately tied to the growth and activity of the largest black holes in the universe. This second clearing act provides cosmologists with an incredibly valuable tool, a unique probe into the thermal history of the intergalactic medium. Because helium's second electron is so difficult to remove, the process of He-Roman-2 reionization deposits a tremendous amount of heat into the gas. When a high-energy photon ionizes a He-Roman-2 atom, the liberated electron shoots away with a lot of kinetic energy, which is quickly shared with neighboring particles through collisions, heating the entire region. This wasn't a gentle warming, it was a significant injection of energy that left a distinct and measurable thermal signature on the IGM. By studying the properties of the gas from this era, particularly through the helium version of the Lyman-alpha forest, scientists can essentially take the temperature of the universe at a very specific time in its history. This allows them to trace the precise timing and intensity of this event in a way that is much more difficult for the earlier hydrogen reionization. Yet, for all its potential as a cosmic thermometer, the He-Roman-2 reionization remains deeply controversial. The central puzzle lies in its timing and its drivers. Observations of the He-Roman-2 Lyman-alpha forest in the spectra of rare, bright quasars show that the process was highly incomplete and patchy at redshift 3.5, but mostly finished by redshift 2.8. This suggests it occurred later and was more drawn out than previously thought. But what was the exact cause? Was it truly the brilliant but relatively rare quasars? Or could there have been a significant contribution from hot, massive stars within galaxies? This is the heart of the debate. Quasars are the obvious candidate because they produce copious amounts of the required high-energy light. However, population studies suggest there might not have been enough of them at the right time to fully reionize all the helium so quickly. This has led some scientists to propose that hot, evolved stars in galaxies, such as those responsible for X-ray binaries, could have provided a crucial, steady background of X-rays that contributed significantly to the process. The challenge in solving this puzzle is immense, primarily because observing He-Roman-2 reionization is extraordinarily difficult. To see it, astronomers need to look at a very specific, high-energy wavelength of light that is almost completely absorbed by our own galaxy's interstellar medium. This requires putting telescopes above Earth's atmosphere, and even then, only the most sensitive instruments can detect the faint signal. The few precious spectra we have come from a handful of extremely bright quasars that act as backlights, and each line of sight tells a slightly different story, some showing clear bubbles of ionized helium and others showing dense regions that are still neutral. This variance makes it hard to pin down a universal timeline, suggesting the process was uneven, with some parts of the universe being illuminated later than others depending on their proximity to a powerful quasar. Resolving the He-Roman-2 reionization puzzle is about more than just completing the story of ionization. It's about accurately weighing the influence of the universe's most powerful engines. Did the growth of supermassive black holes and their resultant quasars dominate the energy output of the universe during this critical period? Or was it a more collective effort involving the stellar populations of entire galaxies? The answer will tell us what truly shaped the intergalactic medium during its middle age, and how the incredible energy from these sources governed the thermal state of the cosmos, influencing the flow of gas and the future of galaxy formation for billions of years to come. To truly appreciate the intergalactic medium, we must view it not as a static scene but as a character in an epic story, one that has undergone a radical transformation over nearly 14 billion years. Its cosmic evolution is a grand narrative of change, from a simple, uniform beginning to the complex and structured entity we detect today. This journey starts in the universe's infancy, immediately after the Big Bang, when space was filled with a searingly hot, dense plasma of particles. As expansion cooled the cosmos, this plasma settled into a thick, neutral fog of hydrogen and helium atoms, a state of profound simplicity and darkness. For hundreds of millions of years during the cosmic dark ages, this was the entire story, a quiet, opaque universe waiting for its first light. The turning point arrived with the birth of the first stars and galaxies, whose intense radiation began the great work of reionization. This was the IGM's phase change, a universal transformation from a neutral fog to an ionized plasma. But the crucial mystery lies in the details of this evolution. We might assume this change happened uniformly, governed by the smooth, universal laws of physics acting everywhere at once. However, mounting evidence suggests the story is far messier and more intriguing. The intergalactic medium did not evolve in a single, coordinated wave. Instead, it changed at different times and at different rates depending on where you look. This patchwork history implies that local conditions, the presence or absence of brilliant quasars, the density of early galaxies, the specific geometry of the cosmic web, played an overpowering role in shaping the development of the cosmos, challenging the idea that the universe's evolution is a simple, predictable clockwork. This idea of a variable cosmic evolution is powerfully illustrated by the enduring mystery of the helium reionization we just explored. While hydrogen reionization was a widespread event likely driven by countless early stars, the second ionization of helium appears to have been a more localized affair. In regions of space that were lucky enough to be near a brilliant hard-spectrum quasar, the intergalactic helium was stripped of its last electron early on. In more quiet, isolated voids, the helium might have remained singly ionized for billions of years longer. This creates a cosmic map where the history of the IGM is written in patches, its state dependent on the chance placement of the universe's most energetic engines. The variations run even deeper than this. When we compare the Lyman-alpha forests from quasars in different directions, we find that the density and temperature of the gas are not the same. One line of sight might show a spectrum packed with absorption lines, indicating the light passed through a dense filament of the cosmic web. Another might show a clean spectrum, meaning it journeyed mostly through an empty void. This tells us that the IGM's structure, and therefore its evolutionary path, is inherently lumpy. The gas in dense regions collapsed early under gravity, heating up through shocks and becoming part of the warm-hot intergalactic medium. Meanwhile, gas in the voids remained more pristine, cooler, and less disturbed for much longer. The evolution of the IGM in a crowded supercluster was a violent, energetic drama. Its evolution in a lonely void was a quiet, slow-motion story. This leads to a profound implication for our understanding of cosmic laws. We operate on the assumption that the universe is homogeneous and isotropic, that it looks roughly the same in every direction, and that the same physical laws apply everywhere. This Copernican principle is a cornerstone of modern cosmology. The varying evolution of the IGM doesn't break these laws, but it demonstrates that their outcomes are not uniform. The laws of physics are the same in a void as they are in a filament, but the initial conditions are wildly different. Gravity acts the same everywhere, but its ability to pull matter together depends entirely on how much matter was there to begin with. Radiation physics is constant, but its power to ionize and heat depends on the distance to the nearest quasar. The IGM story is one of universal laws producing intensely local results. Unraveling this variable history is like trying to piece together the biography of an entire civilization by reading random pages from diaries found in different cities. Each quasar spectrum gives us a detailed timeline for one specific needle-thin path through the cosmos. To get the full picture, we need a colossal number of these samples. This is the driving force behind enormous, ambitious sky surveys like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument. By collecting spectra from millions of quasars, astronomers are not just mapping the structure of the universe, they are compiling a vast library of evolutionary stories. They can finally begin to see the patterns emerge, how the ionization state correlated with galaxy density, how the temperature of the gas increased in regions with more frequent supernova shocks, and how the entire intergalactic medium cooled overall as the universe expanded, but with fascinating regional exceptions. Ultimately, the evolving intergalactic medium is the ultimate record keeper. Its temperature, ionization state, and chemical composition are a living archive, storing the energy output of every quasar that has ever flared and every galaxy that has ever formed stars. By learning to read this archive, we are doing more than just studying empty space. We are writing the history of all structure in the universe. Its patchy, uneven evolution is not a complication to be ignored, but the central clue to understanding how the cosmos truly grows, revealing a story where chance, location, and local violence are just as important as the fundamental constants of physics in shaping the reality we see today. Yet for all its theoretical importance, the warm-hot intergalactic medium remains the most tantalizing and elusive component of the cosmic web, a ghost we know must be there but can't quite seem to pin down. The challenge of definitively catching it isn't for lack of trying. It's a problem rooted in the fundamental limits of our technology and the sheer subtlety of the signal we're chasing. Imagine trying to hear a single, quiet conversation happening in a crowded, roaring stadium. That's the scale of the difficulty facing astronomers in their hunt for the WHIM. The primary hurdle is the nature of the WHIM itself. This isn't a cloud of cool, neutral hydrogen that leaves a sharp, dark fingerprint on a quasar spectrum. This is gas that has been heated to millions of degrees, so hot that it exists as a thin, ionized plasma. Gas this hot doesn't emit much light in the visible or ultraviolet range. Instead, it glows faintly in high-energy X-rays. But this glow is incredibly feeble. The WHIM is so incredibly diffuse, with densities perhaps only a few hundred atoms per cubic meter, that its X-ray emission is drowned out by virtually every other source in the sky. It's like trying to spot the faint, heat-induced shimmer rising from a desert highway from an airplane cruising at 30,000 feet. The signal is there, but it's vanishingly weak against the bright background of the world below. This leads directly to the limitations of our current telescopes. To detect this faint X-ray whisper, we need instruments with immense collecting area, essentially very big ears to hear that quiet conversation. Our current X-ray observatories, like Chandra and XMM Newton, are engineering marvels, but they simply aren't large enough to collect the vast number of photons required to see the WHIM emission clearly. They can only detect it in the most extreme and favorable circumstances, such as where the filaments of the cosmic web are squeezed and compressed by the gravitational pull of a massive galaxy cluster, making the gas slightly denser and brighter. For the vast majority of the WHIM, its emission is too faint for these telescopes to see against the pervasive X-ray background noise. So if we can't easily see the WHIM glow on its own, the main strategy has been to look for it in absorption. This is the same technique used to find cool gas, but it's far more difficult, as the light from a brilliant X-ray source like a quasar travels through a filament of the WHIM. The highly ionized atoms in that gas, things like oxygen-7 or neon-9, should absorb very specific wavelengths of that light. The problem is twofold. First, there are very few X-ray bright quasars positioned perfectly behind a suspected WHIM filament to use as a backlight. Second, the expected absorption lines are exceedingly shallow and broad, blending into the noise of the quasar's own spectrum. Distinguishing a true WHIM absorption line from random instrumental fluctuations or from unrelated absorption by much closer gas in our own galaxy is a monumental statistical challenge. It requires painstakingly adding together the signals from multiple quasar sightlines, hoping that a consistent pattern emerges. This issue of foreground contamination is a relentless foe. Our view of the distant WHIM is filtered through the entire contents of our own Milky Way galaxy, which is filled with its own hot, ionized gas. Before we can claim a detection of the intergalactic WHIM, we must first perfectly model and subtract the absorption signatures coming from our galactic neighborhood. It's an astronomical version of trying to listen for a faint sound from outside your house while your refrigerator is humming loudly. You have to know the exact pitch and timbre of the refrigerator's hum to filter it out. Any error in that model can either create a false signal or erase a real one. The promise of a solution, however, shines brightly on the horizon, carried by a new generation of telescopes designed specifically for this hunt. Missions like ESA's Athena, the X-ray observatory, slated for launch in the 2030, will be a game-changer. With a collecting area orders of magnitude larger than current telescopes, Athena will be like moving from a desktop telescope to the world's most powerful observatory. It will have the sensitivity to not only detect the faint absorption lines of the WHIM with confidence, but also to potentially map its emission in unprecedented detail, tracing the outline of the cosmic web itself. Similarly, advanced ultraviolet telescopes concepted for the future will probe the lower temperature interfaces of the WHIM, offering a complementary view. These instruments won't just be looking for one definitive proof. They will gather thousands of observations, building a statistical picture so robust that the WHIM will finally transition from a theoretical prediction to a mapped component of our universe. Solving this decades-old mystery will do more than just find the missing baryons. It will open an entirely new window into the dynamic and energetic processes that have shaped the cosmos. This incredible journey of galactic pollution brings us face to face with one of the most fundamental and stubborn problems in all of modern astrophysics, the feedback problem. We've seen how stars and black holes act as cosmic engines, spewing energy and enriched material into the void. But how exactly do these relatively small-scale events, confined to the chaotic centers of galaxies, manage to influence the entire intergalactic medium, a volume of space so immense it defies comprehension? This is the core of the mystery. It's the cosmic equivalent of understanding how a single, powerful speech in a small town square could somehow change the political climate of an entire continent. The mechanisms are not just poorly understood, they represent a critical failing in our most sophisticated models of the universe. At its heart, feedback is the process by which galaxies self-regulate. A galaxy forms stars. Those stars eventually explode, heating the surrounding gas and blowing it away, which then shuts off further star formation until the gas can cool and fall back in. It's a cosmic thermostat, but in our computer simulations, this thermostat is incredibly difficult to get right. The energy from a supernova or a quasar's jet is so immense that when we input the correct physics into our models, the result is often catastrophic. Instead of a gentle, regulating wind, the feedback frequently acts like a bomb, blowing all of the gas out of the galaxy in a single, violent event, permanently shutting down star formation and leaving behind a galactic corpse that doesn't match what we actually observe in the real universe. The gas either doesn't get pushed far enough or it gets pushed too far. Getting it just right, ejecting enough material to enrich the IgM and slow star formation without completely sterilizing the galaxy, requires a level of fine-tuning that makes physicists deeply uncomfortable. It suggests that our understanding of how energy couples to the gas is incomplete, that we're missing a crucial piece of physics. So what are the hidden variables in this equation? One compelling idea points to the structure of the interstellar medium itself. The gas within a galaxy isn't a smooth, homogeneous cloud. It's more like a complex sponge or a froth, filled with dense, cold clouds surrounded by vast bubbles of hot, ionized plasma. When a supernova explodes, its energy doesn't hit a solid wall of gas. It preferentially travels through the path of least resistance, channeling through the hot bubbles and potentially breaking out of the galaxy much more efficiently than if it had to plow through a uniform medium. This means the same amount of explosive energy could have wildly different effects depending on the small-scale structure of the gas, a level of detail that is currently impossible to include in cosmological scale simulations. It's the difference between trying to predict how a wave will travel across a calm ocean versus how it will behave crashing through a labyrinth of rocky channels and inlets. Another layer of complexity involves magnetic fields, which we know thread through the interstellar and intergalactic medium. These fields could act as a conduit, helping to transport energy from the galactic center out into the halo and beyond more efficiently. Alternatively, they might provide a form of scaffolding that helps contain the energy for a brief period, allowing it to do its work of heating and pushing gas without simply bursting out. There's also the role of cosmic rays, high-energy particles accelerated by supernova shocks and black hole jets. These particles don't just deposit their energy instantly. They can travel large distances along magnetic field lines, diffusing through the galaxy and depositing their energy gradually and over a wider area, providing a more distributed and gentle form of pressure that might be the missing ingredient for realistic feedback. The challenge of observing feedback in action adds to the mystery. We see the evidence for it everywhere in the massive outflows of gas detected around starburst galaxies and active quasars, and in the polluted state of the IGM itself. But catching the precise moment when energy is transferred and measuring its efficiency is incredibly difficult. It requires resolving phenomena that occur on scales of light years within galaxies that are millions of light years away. New instruments like the James Webb Space Telescope and the upcoming extremely large telescopes are beginning to peer into the hearts of these galactic winds. But for now, the conversion process, how thermal energy becomes kinetic energy, how much is radiated away, and how much is used to do the work of pushing gas remains a black box in our models. Consequently, astrophysicists are forced to use a workaround. Since they can't yet simulate the exact physics, they instead use sub-grid recipes. They tell their simulations, in effect, we don't know how it works, but we know that for a galaxy of this mass with this star formation rate, this amount of energy should be injected back into the gas. They then adjust these knobs until the simulation produces a universe that looks like our own. It's a pragmatic solution, but it's a constant reminder of our ignorance. The feedback problem, therefore, is more than just a technical hurdle. It is a profound gap in our understanding of how the universe operates. It sits at the messy intersection of the immense scales of cosmology and the chaotic, small-scale physics of plasmas and turbulence. Solving it is the key to moving from a universe that we can roughly simulate to one we can truly understand, revealing how the brilliant, violent lives and deaths of stars and black holes echo across billions of light years, shaping the cosmic web and writing the rules for the birth and death of galaxies themselves. But to find the most extreme and telling examples of this ongoing chaos, we must travel to the universe's greatest construction sites, the places where gravity is working overtime. These are the proto-cluster environments, vast regions of space that are destined to become the most massive structures in the cosmos, the immense galaxy clusters of the future. If the cosmic web is the universe's skeleton, then these are its emerging joints and vertebrae, the places where multiple dense filaments intersect and where matter is piling up at a breathtaking rate. The intergalactic medium in these special zones is unlike anywhere else. It is a preheated, pre-polluted, and wildly energetic environment that presents us with a fascinating chicken and egg mystery. We can see that the gas here is already hotter and denser long before the cluster's famous hundreds of galaxies have fully assembled, and before its central black hole has grown to a truly monstrous size. The question is, what fired up the furnace so early in the construction process? The signature of this preheating is unmistakable when we manage to observe it. Astronomers target the most distant massive clusters they can find, looking back to a time when these structures were still coming together. Using powerful X-ray telescopes, they can detect a faint, diffuse glow between the young galaxies, a telltale sign of a very hot, thin plasma. The temperature of this gas can reach tens of millions of degrees, a sure sign that tremendous energy has already been dumped into it. Furthermore, spectroscopy reveals that this proto-cluster medium isn't pristine. It's already laced with heavy elements like oxygen and iron. This is the real head-scratcher. The galaxies within the proto-cluster are still young themselves, many of them just beginning their star-forming lives. They shouldn't yet have had the time, through successive generations of supernova, to produce and eject such a vast quantity of enriched material out into the space between them. The environment is already mature, acting like a fully formed cluster, while its constituent galaxies are still in their cosmic infancy. So what cosmic forces could possibly be responsible for this advanced state of the intergalactic medium? The prime suspect is a process known as gravitational heating. As dark matter pulls these vast rivers of gas into the deepening potential well of the future cluster, the gas doesn't flow smoothly. It slams into itself at incredible speeds, creating enormous shock waves, cosmic sonic booms that reverberate through the region. These shocks violently compress the gas, heating it in the process, much like how a bicycle pump gets hot when you compress the air inside it rapidly. This could account for the intense temperatures we observe, a form of large-scale friction generated by the sheer violence of the structure's assembly. It's a top-down heating process driven by the overarching architecture of the cosmic web itself, rather than by the individual galaxies within it. But gravity alone might not be enough to explain the early chemical enrichment. For that, we must look to the most extreme galaxies within the protocluster. Even at these early times, these dense environments seem to accelerate galactic evolution. The first galaxies to form in the densest knots of the dark matter web might experience a ferocious burst of star formation, living fast and dying young. Their short, brilliant lives could end in a coordinated chorus of supernova explosions, whose combined energy might be powerful enough to blow enriched material out of the galaxy's shallow gravitational wells and into the protocluster medium. Furthermore, the same conditions that foster rapid star formation might also lead to the quick growth of supermassive black holes. If even one of these becomes an active quasar, its incredible energy output could flood the entire protocluster region with radiation and powerful jets, further heating the gas and seeding it with metals manufactured in the black hole's accretion disk. In this scenario, a handful of precocious, hyperactive galaxies act as the caterers for a cosmic gala that is just getting started, preparing the environment for the thousands of guests that have yet to arrive. The profound implication here is that your fate in the universe is determined by your zip code. A galaxy forming in one of these dense protocluster environments is born into a ready-made hot atmosphere. This has a dramatic effect on its entire life story. The hot, high-pressure intergalactic medium acts as a barrier, making it more difficult for fresh, cool gas from the cosmic web to flow in and fuel new star formation. This can strangle a galaxy prematurely, causing its star-forming life to be shorter and more intense than that of a similar galaxy in a quieter rural void. The environment itself, heated and enriched by the earliest arrivals, sets the rules for all future growth. This means that to understand any individual galaxy, we must first understand the history of its neighborhood, a history that begins not with the galaxies themselves, but with the mysterious early conditioning of the intergalactic medium in which they are embedded. This constant, invisible rain of ancient light might seem entirely separate from the story of the gas between the galaxies, but in reality, they are locked in a subtle and revealing dance. The cosmic microwave background and the intergalactic medium are not just cohabitants of the cosmos. They interact in a way that allows us to map the unseeable, creating a shadow puppet show on the grandest possible stage. The phenomenon that makes this possible is one of the most clever tools in the cosmologist's kit, an effect that turns the CMB's perfect canvas into a detailed chart of the universe's hidden matter. It's called the Sunyaev-Zeldovich effect, and it begins with a seemingly insignificant event, a single photon of CMB light bumping into a single superheated electron. To understand this, picture the cosmic microwave background as a perfectly smooth sea of microwaves, a relic fossilized from a time when the universe was a hot plasma. Now imagine a massive cluster of galaxies. The space between the galaxies in that cluster isn't empty. It's filled with the ionized, multi-million-degree gas of the intergalactic medium, a plasma teeming with fast-moving electrons. As the CMB photons travel across the universe and pass through this cluster, they have a chance of colliding with these electrons. This isn't a destructive crash, it's a scattering event. The much more massive electron gives the tiny photon a kick, a boost of energy, much like a ping-pong ball being hit by a baseball bat. This interaction, happening trillions upon trillions of times, leaves a specific and measurable imprint on the CMB light that has passed through the cluster. The genius of this effect is what it does to the CMB spectrum. The CMB has a very specific blackbody spectrum, a perfect curve that peaks in the microwave range. When photons are boosted to higher energies by these hot electrons, they are effectively stolen from the lower energy part of the spectrum and added to the higher energy part. The result is a distortion. At the longer wavelengths where the CMB is normally brightest, we see a slight dimming, a shadow. But at shorter, higher energy submillimeter wavelengths, we see a corresponding brightening. This unique spectral signature is the undeniable fingerprint of the Sunyaev-Zeldovich effect. It doesn't just tell us that a galaxy cluster is there. It tells us that the cluster is filled with a huge reservoir of incredibly hot ionized gas. Crucially, the strength of this distortion depends directly on the pressure of the electron gas, which is a product of both its density and its temperature. This allows astronomers to essentially weigh the hot gas in a cluster, and the answer is always staggering. There is far more mass in this diffuse intergalactic plasma than there is in all the stars of all the cluster's galaxies combined. This makes the SZ effect an unparalleled tool for discovery. Unlike optical or X-ray telescopes, which rely on detecting light emitted by the gas itself, this technique works by seeing the gas in silhouette against the brilliant backlight of the CMB. This means its effectiveness doesn't diminish with distance. A faint, distant cluster that would be invisible to an X-ray telescope because its emission is too weak can still cast a clear and measurable shadow on the CMB, a shadow that is just as distinct as one from a nearby cluster. This has allowed cosmologists to find some of the most massive, distant structures in the universe, building vast catalogues of galaxy clusters that are used to test our models of cosmology and dark energy. It is quite literally a way to see the invisible. However, as with all great cosmic discoveries, this powerful tool has revealed its own set of puzzles. The most significant one concerns the distribution of this hot gas. When astronomers use the SZ effect to measure the gas pressure in clusters and compare it to measurements from other techniques, like gravitational lensing, which maps the total mass including dark matter, things don't always add up perfectly. The hot gas seems to be distributed in a way that doesn't perfectly trace the underlying gravitational potential of the dark matter halo. In the outskirts of clusters, the gas appears to be clumpier and more turbulent than our smooth, gravitational models predict. It seems that non-gravitational forces, the very feedback processes from supernova and active black holes we struggle to model, are stirring the pot, redistributing the energy and mass of the gas in ways we are only beginning to comprehend. Furthermore, the grand ambition is to use the Sunyaev-Zeldovich effect to map not just the gas in obvious clusters, but the faint, tenuous filaments of the Warm-Hot Intergalactic Medium itself. This is the final frontier for this technique. The WHIM is so diffuse that its electron pressure is minuscule, creating an SZ distortion that is buried deep within the noise of the CMB measurements. Isolating this signal would be the ultimate proof of the cosmic web structure and the definitive solution to the missing baryon problem. Experiments are tirelessly working to tease out this faint signature by stacking data from thousands of suspected filament locations, hoping to find a consistent statistical whisper of distortion. Success would give us a three-dimensional map of the universe's skeleton, drawn not in light, but in the subtle shadows it casts on the oldest light there is. This interaction between the ancient afterglow and the modern interstellar ocean is a beautiful demonstration of cosmic interconnection, proving that even the most primordial relics can be used to illuminate the present-day structure of everything. We've mapped the visible gas and inferred the gravitational pull of dark matter, but could there be entire reservoirs of material hiding within the intergalactic medium that are completely invisible to every tool at our disposal? This brings us to a truly frontier mystery, a speculation that pushes at the very boundaries of known physics, the possibility of dark gas reservoirs. What if the missing baryons we've been hunting are not just hot and difficult to see, but are hiding in a form we haven't even thought to look for, composed of matter that behaves in ways entirely foreign to our experience? One of the most intriguing theoretical ideas involves dark matter itself. Our standard model of cosmology treats dark matter as cold and collisionless, meaning its particles only interact with ordinary matter and with each other through gravity. They are ghostly spectators flowing through planets and people without a whisper. But what if that isn't the complete picture? Some physicists propose scenarios where a small fraction of dark matter particles do interact with each other through a new, unknown force, a so-called dark force. Under the right conditions, this self-interacting dark matter could clump together not just gravitationally, but form dark atoms, dark molecules, and even dark planets or stars made of this exotic substance. While this wouldn't account for the missing normal matter, it introduces a staggering possibility that the cosmic web's filaments could be interwoven with two separate structures, one of glowing, hot gas and another of a completely invisible, dark chemistry playing out in parallel, its presence only hinted at through subtle gravitational anomalies we can't yet explain. Perhaps even more mind-bending is the thought that the missing matter could be ordinary hydrogen in an exotic state we've never been able to study in a laboratory. Consider the element we think we know so well. On Earth, hydrogen is a gas, a liquid, or a metal under immense pressure. But in the extreme, lonely conditions of the intergalactic void, it might exist in phases that are nothing more than theoretical predictions. One such idea is the concept of metallic hydrogen. Under pressures millions of times greater than Earth's atmosphere, hydrogen is predicted to collapse into a dense, liquid metal that could conduct electricity with perfect efficiency. While we typically associate such pressures with the hearts of giant planets like Jupiter, some theories suggest that vast, cold clouds of hydrogen in the deep voids, collapsing under their own gravity over billions of years, but never quite reaching the density to ignite a star, could form strange, isolated droplets of this primordial metallic substance. These would be dark, dense objects, virtually impossible to see against the blackness of space. Another exotic possibility lies in the realm of quantum physics. At temperatures near absolute zero, which can be found in the most quiescent and expanded regions of space, collections of bosons, a class of particles that includes photons, can collapse into a single quantum state known as a Bose-Einstein condensate. Could vast, diffuse clouds of hydrogen atoms, cooled over eons and undisturbed by shocks or radiation, undergo a similar phase transition? The result would be a cosmic-scale superfluid, a single, coherent quantum object with bizarre properties, perhaps frictionless and incapable of emitting or absorbing light in the ways we expect. A structure like this would be a true phantom, a ghost in the cosmic machine that gravitationally influences its surroundings while remaining completely undetectable by conventional electromagnetic means. The challenge and the fascination with these ideas is their sheer intractability to observation. How do you search for something when you don't know what its signature might be? The hunt for these dark reservoirs is necessarily indirect, often relying on secondary effects. Astronomers might look for unexpected gravitational lensing effects, the subtle bending of light from distant galaxies, that cannot be accounted for by the visible mass of a gas cloud or a dark matter halo alone. They might search for strange absorption features in the spectra of quasars that don't match the fingerprints of any known atom or molecule. Or they might look for the telltale disappearance of light from distant sources in a way that suggests not merely absorption, but a complete conversion into something else entirely. These concepts reside firmly at the edge of known science, a blending of established cosmology with speculative particle physics and condensed matter theory. They are not the mainstream explanation for the missing baryons, but they serve a vital purpose. They force us to question our assumptions and remind us that the universe is under no obligation to be simple or easily understood. The history of astronomy is filled with discoveries that began as seemingly outlandish speculations. The confirmation of such a dark reservoir would be a revolution on par with the discovery of dark matter itself, revealing an entirely new chapter in the story of cosmic structure and proving that even the most fundamental components of our reality can still hold profound and shocking secrets. Now imagine a light that doesn't come from any single star or galaxy, but from all of them at once, a cosmic glow so faint and diffuse that it's invisible to our eyes, yet it fills every cubic centimeter of the universe. This is the cosmic ultraviolet background, a mysterious and pervasive sea of energy born from the combined light of countless trillions of stars, quasars, and galaxies, all shining across space and time. It is the universe's ambient lighting, and it plays a role just as crucial as gravity in shaping the fate of the gas between the galaxies. This background isn't a relic from the Big Bang like the cosmic microwave background. It's a living, dynamic entity constantly being generated and renewed. Every star that has ever burned, every quasar that has ever flared, contributes its own small share of ultraviolet photons to this collective ocean. These photons then travel for billions of years, their paths winding through the cosmic web until they eventually interact with a lonely atom of hydrogen or helium drifting in the void. When that happens, they don't just bounce off, they deliver a powerful kick, enough to rip an electron free in a process of continuous ionization. This is the cosmic UV background's primary job. It acts as a universal maintenance crew, ensuring that the hydrogen in the intergalactic medium stays ionized long after the initial epoch of reionization concluded. Without this constant, subtle rain of energy, the electrons and protons would eventually find each other and recombine, and the universe would slowly fog over again. This background radiation is what keeps the cosmos transparent for our telescopes, but its influence goes far beyond just ionization. Every time a photon ionizes an atom, the liberated electron flies away with a significant amount of kinetic energy. This energy is quickly shared with neighboring particles through collisions, effectively heating the entire surrounding gas. This makes the cosmic UV background a primary heating source for the intergalactic medium, a ubiquitous cosmic microwave that sets a fundamental floor temperature for the universe. The temperature of a gas cloud determines its fate. Hot gas resists collapse, while cooler gas can condense and form stars. Therefore, this unseen background glow is silently regulating the rate of star formation across the entire cosmos, influencing the growth of galaxies from the inside out by controlling the state of the fuel that might eventually fall into them. The profound mystery, however, is that we have no way to point a telescope directly at this light and measure it. Because it comes from every direction simultaneously, it has no single source. It's the ultimate diffuse glow. Instead, astronomers must become cosmic detectives, looking for its fingerprints on the things it touches. The primary evidence comes once again from the Lyman-alpha forest. The precise thickness and structure of the absorption lines in a quasar's spectrum are exquisitely sensitive to the intensity and color of the ultraviolet background. A stronger background would ionize more hydrogen, leading to fewer and weaker absorption lines. A background richer in higher energy photons would heat the gas more, creating broader, smoother lines. By carefully analyzing thousands of these spectra, scientists can essentially work backwards, inferring the properties of the illuminating source. This is where the puzzle deepens considerably. The answers they get are confusing and often contradictory. Different lines of sight suggest different intensities for this background radiation. Some regions of space seem to be bathed in a stronger UV glow than others. This shouldn't be possible for a phenomenon that is, by definition, universal. The leading explanation for this variance points back to the patchiness of the sources themselves and the shadowing effect of the cosmic web. Just as clouds can block sunlight, dense filaments of neutral hydrogen can absorb UV photons, creating localized shadows in the background radiation. A gas cloud sitting in the shadow of a large cosmic filament would experience a much weaker UV field than a cloud floating in an open void, and this would dramatically affect its temperature and ionization state. Our single straw-like view from a quasar spectrum might be sampling a brightly lit region, while another might be sampling a shadowy one, leading to a bewildering range of measurements. The second major uncertainty lies in the background spectrum, its color. We don't know exactly what mix of objects provides the majority of this light. Does it come mostly from the immense number of relatively cool stars in galaxies, or is it dominated by the fierce, hard radiation from quasars and active black holes? The answer matters immensely because different types of light have dramatically different effects. The soft UV light from stars is excellent at ionizing hydrogen, but it doesn't penetrate very far through dense gas. The hard UV and X-ray light from quasars, on the other hand, can travel much deeper into cosmic voids and is also responsible for ionizing helium. Our models of how the intergalactic medium evolves are built on an assumed spectrum for this background, and if we have the wrong recipe, our entire understanding of the thermal history of the universe could be fundamentally off. It's like trying to predict how quickly a room will heat up without knowing if the heat is coming from a gentle space heater or a blowtorch. This uncertainty creates significant and cascading errors in our simulations. The rate at which gas cools, the efficiency of star formation in small galaxies, and even the distribution of those missing dwarf galaxies are all heavily influenced by the assumed properties of the UV background. If we overestimate its intensity, our simulated gas becomes too hot and too ionized, preventing galaxies from forming. If we underestimate it, too much gas remains cool and neutral, leading to an overabundance of small galaxies. Modelers are constantly adjusting this parameter, this unseen universal light, to make their digital universes look like our own. But without a ground truth measurement, it remains one of the largest sources of error in computational cosmology. The cosmic ultraviolet background is thus a magnificent paradox. It is both one of the most important forces shaping the universe and one of the most poorly constrained. It is the ghost in the machine, an invisible hand that we know is guiding the evolution of the cosmos, but whose strength and nature remain just out of view. A fundamental mystery written in the faintest light of all. For all our talk of galaxies as the great engines of the cosmos, we must now completely reverse our perspective. We've seen how stars and black holes inject energy and metals back into the intergalactic medium, but this is only half of a great cosmic dialogue. The other, more mysterious half of the conversation is how the IGM talks back, actively governing the very birth and death of the galaxies themselves. This is not a one-way street of galactic influence. It is a complex feedback loop where the state of the seemingly empty voids between galaxies holds the ultimate power to grant life or impose a permanent silence. The central puzzle is one of a fundamental contradiction. On one hand, we have a universe filled with violent heating processes, the searing radiation from quasars, the shock waves from colliding structures, and the cosmic ultraviolet background. This energy constantly works to keep the intergalactic gas hot, ionized, and energized, preventing it from collapsing. On the other hand, we clearly live in a universe where gas does collapse, cool, and form new stars, and has done so for billions of years. So how does this happen? How does a massive cloud of million-degree plasma, adrift in the void, manage to shed all that energy, cool down, and condense into the delicate nuclear-firing furnaces we call stars? The answer lies in a delicate and precarious cosmic balancing act that is still not fully understood. The journey of gas from the diffuse IgM to a shining star is a story of loss, the loss of energy. For gas to collapse under its own gravity, it must find a way to radiate away its immense thermal energy. The primary mechanism for this is through atomic transitions. An atom in a hot, ionized plasma is excited. It has a lot of energy. When that atom captures a free electron and becomes neutral again, or when a free electron collides with an ion, it can release a photon of light. This photon then travels away into space, carrying the energy with it and effectively cooling the gas. The efficiency of this cooling depends critically on two things: the gas's density and its chemical composition. Denser gas has more atoms to collide and radiate, so it cools faster. And this is where the IgM's history of pollution becomes absolutely vital. Heavier elements like carbon, oxygen, and iron are dramatically more efficient at radiating energy than simple hydrogen or helium. A cloud of gas enriched with even a tiny trace of these metals can cool orders of magnitude faster than a pristine cloud. The very pollution that galaxies spewed out into the void is what makes the continued formation of new generations of stars even possible. It's the universe recycling its own waste into the building blocks of future life. But this is only the first step. For this cooled gas to actually form stars, it must physically reach the galaxy. This is where the cosmic web acts as the universe's grand irrigation system. The filaments of dark matter that form the web's skeleton act as gravitational conduits, funneling gas from the vast reservoirs of the IgM toward the hungry galaxies at the nodes. We used to imagine a simple, spherical collapse of gas onto a waiting galaxy. We now know the process is far more structured and directional. Gas flows along these dark matter highways in relatively cold, narrow streams that can, for a time, penetrate a galaxy's hot outer halo. It's as if the galaxy isn't drawing from a diffuse cloud, but drinking from a series of cold fire hoses that are channeling fuel directly to its star-forming core. Protecting these delicate streams as they travel through the hostile, hot environment of a galaxy's halo is a major challenge for our models. They shouldn't easily survive, and yet somehow they do. This brings us to the great dichotomy. Why do some galaxies continue to form stars at a steady pace for billions of years, while others in seemingly identical environments see their star formation shut down completely, becoming so-called red and dead ellipticals? The emerging answer points directly to the IgM and the galaxy's specific position within the cosmic web. A galaxy's fate is determined by its access to this fresh, cold fuel. A galaxy sitting at a busy intersection of multiple filaments, like in a rich cluster, might have access to a plentiful supply. However, that same environment is also filled with hostile forces. The gravitational tides from nearby galaxies can strip gas away. The immense pressure of the cluster's own hot intergalactic medium, which can reach hundreds of millions of degrees, can act like a powerful wind, physically pushing against incoming gas streams and even blowing the galaxy's own reservoir of gas out into space, a process called ram pressure stripping. In these extreme environments, a galaxy can be starved of fuel or have its gas violently removed, leading to a rapid and premature death. Conversely, a galaxy living in a quieter, more isolated region, a cosmic suburb, might have a slower, more steady supply of gas flowing along a single filament. Without the violent neighborhood, it can hold onto its fuel and form stars at a sustainable rate for much longer. But there's a third, more mysterious state, the galaxy that should have fuel but doesn't. This is where the subtle, pervasive effects of the cosmic UV background and internal feedback create their own form of starvation. For small, low-mass galaxies with weak gravity, the constant, gentle pressure of the ultraviolet background can be enough to keep their gas heated and prevent it from ever cooling down to form stars. For others, a single burst of internal feedback from supernova might blow out all of their gas, and the shallowness of their gravitational well means there's not enough pull to pull it back or attract new gas from the IgM. They are left as dark matter ghosts with a few ancient stars, fossils of a star-forming life that was cut short. This complex interplay means that to understand any single galaxy, we must understand the entire ecosystem it is embedded within. Its history is written not just in its stars, but in the temperature, density, and metallicity of the intergalactic medium that surrounds it. The IGM is the ultimate regulator, the great facilitator, and the great destroyer. It provides the fuel, but it also sets the conditions that determine whether that fuel can be used. It is the context for the story of every galaxy, and we are only just beginning to learn how to read its rules, discovering that the emptiness of space is in fact the most important character in the story of cosmic structure. Venture from the bustling intersections of the cosmic web into its polar opposite, the immense cosmic voids. These are the universe's true deserts, vast regions of space spanning hundreds of millions of light years that are almost completely empty of galaxies, stars, and by all expectations, matter itself. If the cosmic web is the continent, these voids are the open ocean. If the filaments are the mountain ranges, the voids are the deepest, most expansive valleys. Entering a void is like leaving the vibrant coral reef for the open abyss, where the water is clear, quiet, and seemingly lifeless. But in this profound emptiness, the intergalactic medium is at its most pristine, and it holds puzzles that challenge our understanding of how the universe arranges itself on the largest scales. The primary mystery of these voids is a case of unexpected absence. Based on our models of the cosmic web's formation, we expect these regions to still contain some matter. After all, the initial fluctuations from the Big Bang were minuscule. Even the deepest voids should have retained a trace amount of the primordial gas, a thin haze of hydrogen left over from the universe's birth. But when astronomers go looking for this gas, they find even less than predicted. It's as if these regions have been scoured clean by some efficient cosmic cleaning service. The question is, how does matter evacuate these areas so completely? Gravity should work both ways. While it pulls matter into the dense filaments and clusters, it shouldn't be able to make a region of space entirely empty, only much less dense. The extraordinary efficiency of this evacuation process suggests that other, more dynamic forces are at work, actively pushing matter out of the voids rather than just passively allowing it to drain away. The leading theory for this efficient cleanup involves a surprising culprit, the explosive power of supernova and active galactic nuclei, but acting on a truly colossal scale. This is a process known as void pumping. Imagine a void surrounded by the bustling activity of the cosmic web. In the galaxies along the void's boundaries, stars are forming, living, and dying in spectacular supernova explosions. Meanwhile, the supermassive black holes at the centers of those galaxies are erupting, sending out powerful jets and radiation. All of this activity generates immense pressure, literally pushing the surrounding intergalactic medium. This pressurized gas has to go somewhere, and the path of least resistance is directly into the empty void. It might seem counterintuitive, but the galaxies are effectively blowing bubbles of energy that expand into the voids, herding the scant matter that remains there ahead of them and pushing it toward the already dense filaments. It's a form of cosmic urbanization where the developed areas relentlessly expand their suburbs, clearing out the wilderness and driving whatever was there toward the city centers. This continuous pumping action, happening over billions of years, may be what gives the voids their astonishingly clean appearance, leaving behind a vacuum that is even more pure than gravity alone could achieve. This leads to a fascinating property of the void IGM, its incredible state of preservation. The gas that does remain in these deep voids is the closest thing we will ever find to the primordial atmosphere of the universe. It has been largely untouched by the violent cycles of star birth and death that have polluted the rest of the cosmos. It is a time capsule of gas, a sample of what the intergalactic medium was like before it was enriched with the heavy elements forged in stellar furnaces. Studying this gas is like an archaeologist finding a perfectly preserved ancient site that hasn't been disturbed by later civilizations. By analyzing its composition through the subtle absorption lines it imprints on the light of distant quasars, we can measure the fundamental ratios of hydrogen and helium with unprecedented accuracy, testing our predictions for Big Bang nucleosynthesis, the recipe that created the first elements. Any deviation from the expected ratios in this pristine environment would point to new physics operating in the universe's first few minutes. But the mysteries of the void gas don't stop at its composition. The physical conditions within these regions present another profound puzzle. Without galaxies to stir it up and without the shock waves that heat the gas in filaments, the void IgM should be the coldest, calmest place in the modern universe. And to some extent it is. Yet there are hints that even this gas is slightly warmer than our simplest models predict. Why? The subtle, pervasive glow of the cosmic ultraviolet background, that sea of radiation from all the stars and quasars in the universe, may be the answer. Even here, in the deepest void, this radiation penetrates, and it provides a tiny but constant source of heat, preventing the gas from cooling down to the absolute coldest temperatures possible. Measuring the temperature of the void gas, therefore, gives us an indirect way to measure the intensity of this universal background radiation, a measurement that is impossible to make directly. Perhaps the most mind-bending possibility hidden within the voids has nothing to do with normal matter at all, but with dark energy. The accelerated expansion of the universe is driven by this mysterious force, and it operates everywhere. However, in the dense environments of clusters and filaments, the powerful grip of gravity fights a fierce tug of war with dark energy's outward push. But in the voids where gravity's hold is weakest, dark energy is expected to dominate most clearly. Some cosmologists theorize that the voids themselves are not static empty bubbles, but are actually expanding faster than the universe as a whole, stretched by the repulsive force of dark energy from within. If true, this would mean the cosmic voids are not passive empties but active drivers of the universe's ultimate fate. Their growth could be gently pulling the filaments of the cosmic web apart, influencing the large-scale flow of galaxies in ways we are just beginning to model. The voids, therefore, might be the key to understanding the physics of dark energy itself, offering a unique laboratory where its effects can be studied in isolation, free from the complicating grip of strong gravity. In the deepest silence of the cosmos, we might finally hear the clear whisper of the force that will determine everything's end. Now we zoom in from the vast cosmic web to our own local galactic neighborhood, where an entirely different class of mystery floats almost on our doorstep. Drifting through the space between our Milky Way and the Andromeda Galaxy are strange, isolated clouds of hydrogen gas, moving at speeds that defy easy explanation. These are the high-velocity clouds, and they represent a puzzle that has persisted for over half a century, precisely because they are so close yet so difficult to place in our cosmic family tree. The story of their discovery begins not with a towering modern observatory, but with the pioneering work of radio astronomers in the 1960s. As they first tuned their instruments to the 21-centimeter wavelength, the specific frequency emitted by neutral hydrogen, they expected to map the familiar spiral arms of our galaxy. But they found something else entirely, faint, fuzzy patches of gas that were moving at velocities completely unrelated to the orderly rotation of the Milky Way. Some were barreling toward us at hundreds of kilometers per second. Others were speeding away just as fast. Their motion was completely anomalous, suggesting they weren't gravitationally bound to our galaxy's disk. They were uninvited guests at the galactic party, and no one knew where they had come from. The central enigma is one of identity and origin. What exactly are these clouds, and how did they get so close? Astronomers have been arguing over three primary theories for decades, and each one has compelling evidence as well as fatal flaws. The first and most dramatic idea is that these clouds are the long-sought, nearby representatives of the intergalactic medium, itself actual pieces of the cosmic web that have drifted into our local group of galaxies. In this scenario, these would be leftover blobs of primordial gas, pristine hydrogen and helium that never cooled enough to collapse and form stars, and are now falling into the gravitational pull of our galaxy for the very first time. Finding such a cloud would be like discovering a living dinosaur. It would be a sample of the universe's original building blocks, untouched by the polluting fires of stellar fusion. The problem is, when we analyze the light from background quasars shining through some of these clouds, we occasionally detect trace amounts of heavy elements. This suggests they aren't entirely pristine, muddying the waters of this elegant theory. The second major hypothesis connects these clouds to the violent, dynamic interactions between galaxies. Our local group isn't a static place. It's a gravitational ballet featuring the Milky Way, Andromeda, and their entourage of smaller satellite galaxies like the Large and Small Magellanic Clouds. As these dwarf galaxies swing around the larger galaxies, immense tidal forces can literally pull them apart, stretching them into long streams of stars and gas. The high-velocity clouds could be this tidal debris, the cosmic crumbs left over from a galactic meal. There's strong circumstantial evidence for this. The most famous collection of these clouds, the Magellanic Stream, forms a vast arched ribbon of gas that trails behind the two Magellanic Clouds, exactly as predicted by models of tidal disruption. This seems like an open and shut case for at least some of the clouds, yet not all high-velocity clouds are so easily linked to known satellites. Many exist in complete isolation with no obvious parent galaxy, suggesting a more exotic origin. This leads to the third and most extreme possibility, that some of these clouds are not falling in, but are actually being blasted out. This theory casts the high-velocity clouds as the exhaust fumes of our own galaxy. The powerful feedback from supernova explosions in the Milky Way's disk could be launching fountains of hot gas high above the galactic plane. This gas could then cool and condense in the halo, falling back down as relatively cool, dense clouds that we observe as high-velocity objects. In this view, they aren't intergalactic invaders at all, but the product of our galaxy's own intense metabolic cycle, the breath of the Milky Way made visible. The challenge for this model is explaining the clouds with the very highest velocities, which seem to require more energy than our galaxy can typically provide. The reason this debate has raged for so long is that these clouds are deceptively difficult to study. Because they are made of cool, neutral gas, they don't emit light. They only absorb it at that specific 21-centimeter wavelength. This tells us they are there and how fast they are moving, but it reveals very little about their distance. Without knowing precisely how far away a cloud is, we cannot determine its true size or mass, which are the most critical pieces of information for distinguishing between these theories. A cloud that appears large and massive from a distance could, if it were actually much closer, be a small, local phenomenon. Conversely, a faint, small-looking cloud could be a massive intergalactic structure lying far beyond the Milky Way's halo. It's like trying to judge whether a light in the sky is a low-flying airplane or a distant star. Without knowing its distance, you're left guessing. Modern astronomy is finally bringing new tools to bear on this old mystery. Precision measurements of the cloud's internal motions, combined with more sophisticated models of galactic interactions, are slowly helping to pin down their distances. By finding faint stars that are physically associated with some of these clouds, astronomers can use the stars as distance markers, finally tethering the ghosts of gas to a specific location in space. Each new piece of data seems to suggest that there is no single answer. The high-velocity cloud population is likely a mixed bag. Some are tidal debris, some are galactic fountain fallout, and a precious few might indeed be genuine relics of the primordial intergalactic medium, falling into our galaxy for the very first time and offering us a direct taste of the pristine cosmos that existed long before the first stars were born. That ancient rain of material from the earliest stellar explosions did not result in a uniform, well-mixed cosmic soup. Instead, the intergalactic medium is a breathtaking tapestry of chemical diversity, a universe of stark contrasts where some regions are heavily polluted with the ashes of dead stars and others remain almost untouched, pristine relics of the Big Bang. This uneven distribution is the IGM's chemical diversity mystery, and it forces us to ask how elements can be so unevenly spread across billions of light years, creating a cosmic landscape of enriched valleys and primordial mountains. The primary tool for mapping this diversity is once again the incredible absorption line spectrum of a distant quasar. But now, astronomers aren't just looking for the hydrogen lines that form the Lyman-alpha forest. They are hunting for the far fainter, rarer fingerprints of heavy elements. Each element absorbs light at its own unique set of wavelengths, creating a barcode that reveals its presence. When we find a strong absorption line from, say, carbon or oxygen, we know that particular cloud of gas has been enriched. The real surprise comes when we compare different clouds along the same line of sight, or clouds in completely different parts of the sky. The differences can be dramatic. One filament might show a chemical signature as rich as our own sun's neighborhood, indicating it has been thoroughly seeded by countless supernovae. Another cloud, perhaps just a few million light years away in a deep void, might show only the barest trace of metals or even none at all, a clear sign that it has miraculously avoided the polluting winds of galaxies for over 13 billion years. This patchwork quilt of chemistry tells a complex story of cosmic delivery logistics. How do you distribute a few atoms of oxygen across a volume of space that is millions of light years across and overwhelmingly empty? The process is neither efficient nor uniform. Imagine a single supernova exploding in an early galaxy. It launches a cloud of enriched debris at tremendous speed, but that cloud is expanding into a near-perfect vacuum. It might travel for 100 million years, thinning out all the while before it even begins to mix with the truly intergalactic medium. By the time it does, its metals are so diffuse that they might only raise the average metallicity of a vast volume by an infinitesimal amount. Now consider that this must happen billions of times with overlapping bubbles of enrichment from galaxies of all sizes to create the levels we see. The resulting pattern would naturally be incredibly lumpy, with the highest concentrations found near the busiest galactic factories and the lowest levels in the most remote cosmic hinterlands. This isn't just a matter of distance, however. The chemical fingerprint itself varies, and this is where the mystery deepens into a form of cosmic forensics. The ratio of different elements acts as a clock and a tag, revealing the type of stars that did the polluting and how long ago they died. For example, alpha elements like oxygen and magnesium are produced rapidly in the core collapse supernova of short-lived massive stars. An environment enriched primarily by these supernovae will have a high ratio of alpha elements to iron. Iron itself, along with heavier elements, is produced more slowly over time in type Ia supernova, which involve the explosions of white dwarf stars. A region showing a high iron content relative to oxygen tells us that it was polluted by a stellar population that had time to evolve, where many white dwarfs had formed and subsequently exploded. By reading these ratios in the IGM, we can effectively perform an archaeological dig into the history of entire regions of the universe, determining the dominant types of the first stars and the timing of the earliest enrichment events without ever directly seeing those ancient galaxies. The existence of pristine gas, however, is perhaps the most profound part of this mystery. The fact that any of it remains is a testament to the sheer immensity and emptiness of cosmic voids. For a cloud of gas to remain completely untouched, it must have resided in a region that has never felt the shock wave from a nearby supernova or been washed over by the radiative wind from a quasar. It has had to avoid being incorporated into any galaxy, large or small, for the entire history of the universe. These pristine pockets are the ultimate time capsules, and finding them is a primary goal for cosmologists. Their pure hydrogen and helium composition provides a critical baseline measurement against which all theories of Big Bang nucleosynthesis are tested. Any deviation from the predicted ratios in this gas would point to physics beyond our standard model, making these silent, empty voids the setting for some of the most stringent tests of our fundamental understanding of the cosmos. This incredible chemical diversity, from the heavily polluted to the utterly pristine, completes our picture of the intergalactic medium not as a passive backdrop, but as a dynamic and evolving archive. Every element, every ratio, every patch of enrichment is a sentence in the biography of the galaxies. It records their births, their lives of furious stellar formation, their explosive deaths, and their lasting impact on the cosmos around them. This uneven chemical map is the direct result of a delivery system that is at once catastrophically violent and impossibly gentle, capable of hurling millions of suns worth of material across galactic distances, yet unable to fully mix it into a uniform blend. It leaves the universe forever diverse, a place where the raw ingredients of planets and life are concentrated in some regions and entirely absent in others, a fundamental unevenness written into the very fabric of space. But for all our focus on the grand, billion-year evolution of the cosmic web, we must now turn our attention to events of a completely different timescale, the cosmic flash in the pan. The intergalactic medium is typically imagined as a place of profound, glacial slowness, where change is measured in eons. Yet, what if it is also periodically scarred by events of unimaginable violence that are here and gone in a geological blink of an eye? This is the mystery of transient IgM phenomena, the possibility that the largest structure in the universe can be temporarily and dramatically altered by the most fleeting of catastrophes. Imagine a single gamma-ray burst, the most powerful explosion known to occur since the Big Bang itself, triggered by the collapse of a massive star or the merger of two neutron stars in a distant galaxy. For a few precious seconds, this event can outshine its entire host galaxy, releasing more energy than our Sun will emit in its entire 10 billion-year lifetime. But this burst of light is just the beginning. The real impact comes from the narrow, ultra-relativistic jets of material and radiation that scream out from the event at nearly the speed of light. If one of these jets is, by chance, pointed directly along a filament of the cosmic web, it would act like a cosmic blowtorch. For a brief period, perhaps just minutes or hours, this jet would pour an incredible density of high-energy photons into the IgM, fully ionizing not just hydrogen and helium, but even stripping electrons from heavy atoms like carbon and oxygen in a process called superlative ionization. This would create a rapidly expanding bubble, a sphere of completely ionized, superheated plasma within the filament. The event is transient, but its fingerprint on the gas could persist for thousands of years before the region gradually cools and recombines, a ghostly remnant of a flash of violence that was over before humanity even learned to farm. Or consider the fury of a quasar undergoing a monstrous outburst. We think of quasars as steady beacons, but evidence suggests their output can be highly variable. A sudden, colossal accretion event onto a supermassive black hole could cause its luminosity to spike by orders of magnitude, flooding its surroundings with a tsunami of ultraviolet and X-ray radiation. This would not be the gentle, steady rain of the cosmic ultraviolet background. This would be a flash flood. Such an event could photo-evaporate nearby dwarf galaxies, boiling away their gas in an instant. It could also heat the surrounding IgM in a much more localized and intense way than the gradual gravitational shock heating, creating a vast, temporary hotspot that would disrupt the delicate flow of gas along the cosmic web for millions of years. The aftermath would be a strange, inverted region, a sphere of hot, diffuse gas surrounding the quasar, while further out, the cooler, denser filamentary structure remains intact. It would be like a bubble of emptiness blown into the cosmic foam. The greatest challenge with these transient phenomena is their ephemeral nature. Our astronomical observations are snapshots, frozen moments in time. The odds of having a telescope pointed at the exact right patch of sky at the exact millisecond a gamma-ray burst jet is carving a channel through a hydrogen filament are astronomically small. So how could we ever hope to detect evidence of such fleeting events? The answer likely lies not in catching them in the act, but in finding their forensic evidence, the lasting scars they leave behind. One promising method is to search for unusual chemical signatures in the Lyman-alpha forest. A region that was recently flash ionized by a gamma-ray burst would have a unique ionization history. As it recools over millennia, the different elements will recombine at different rates, potentially creating a very specific and abnormal pattern of absorption lines that wouldn't make sense through standard, slow process models. It would look like a cosmic crime scene, a patch of the forest where the chemistry is all wrong. Another approach is to look for the telltale signs of the shock waves these events would generate. Even after the initial flash fades, the expanding bubble of hot gas would continue to push outward, creating a spherical shock front that could travel for millions of years. This shock could compress other, unrelated gas clouds, perhaps even triggering star formation in their outskirts, a wave of new births propagating outward from the site of an ancient cataclysm. Finding a perfect spherical arrangement of young stars around an otherwise quiet galaxy could be the lasting monument to a transient event that occurred eons ago. Perhaps the most fascinating implication of transient IgM phenomena is that they could create temporary and utterly bizarre conditions. For a brief window of time within one of these expanding bubbles, the physical properties of the intergalactic medium could be unlike anything else in the present-day universe. The radiation field could be so intense that it forbids atoms from forming, creating a pocket of perfect plasma. Magnetic fields could be amplified and twisted into unique configurations. These would be natural, if short-lived, laboratories for testing physics under extremes we could never hope to replicate. While they might be rare, the sheer size of the universe means such events are likely happening all the time, somewhere in the cosmos. Our entire understanding of the IgM is based on the assumption of slow, steady processes. The realization that it might also be punctuated by these brilliant, catastrophic flashes forces us to consider a cosmos that is not only vast and ancient, but also dynamically violent on timescales so short they defy our ordinary perception of time. Yet for all its apparent dominance, dark matter is a ghost, its presence felt only through its gravitational pull. So how do we map the distribution of something we cannot see? The answer lies in the very substance we've been exploring, the intergalactic medium. The ordinary matter, the baryonic gas, is not the leading actor in this cosmic play. It is a tracer, a luminous paint brushed onto an invisible scaffold. Because this gas is pulled into the same gravitational wells as the dark matter, its distribution should, in theory, perfectly outline the underlying dark matter structure. When we map the density of hydrogen gas through the Lyman-alpha forest or the hot plasma through X-ray observations, we are essentially drawing a diagram of the dark matter cosmic web. This relationship is the foundational assumption behind our entire understanding of large-scale structure, a partnership where visible matter reveals the invisible. However, this partnership is not always a perfect mirror. As our observations have become more precise, subtle but significant disagreements have emerged, revealing that the relationship between dark matter and ordinary matter is far more complex than a simple gravitational slave and master dynamic. In the immense, relaxed environments of massive galaxy clusters, the two components generally align well. The hot X-ray emitting gas traces the deep gravitational potential carved by the dark matter halo. But when we look at the dynamics of smaller scales, particularly during violent cosmic events, the picture becomes blurred. During colossal collisions between galaxy clusters, like the famous Bullet Cluster, a stunning discrepancy is observed. The bulk of the mass, as mapped by gravitational lensing, is clearly separated from the bulk of the ordinary matter, which is detected through its X-ray emission. The dark matter components of the two clusters seem to have passed right through each other, as expected for a collisionless substance, while the clouds of intergalactic gas were slowed dramatically, much like two clouds of smoke colliding and mingling. This proves definitively that dark matter is not just a different form of ordinary matter. It interacts in a profoundly different way, likely only through gravity. This leads to the central mystery of their connection. If dark matter only guides the gas through gravity, why don't their distributions always match perfectly in quieter environments? Why does the gas sometimes appear to be more spread out or more clumped than the dark matter models predict? The suspicion is that the ordinary matter isn't just passively following orders. It has its own internal dynamics that can push back against gravity's grip. The intense feedback processes we've discussed, supernova winds and AGN jets, inject tremendous energy into the gas, heating it and creating powerful outflows. This can push the baryonic matter around, causing it to expand away from the center of a dark matter halo or even be ejected entirely. In contrast, the dark matter, unaffected by these forces, remains settled in its gravitational well. The result is a galaxy or a region of the IGM where the two components are slightly offset or have different distributions. It's a cosmic tug of war where gravity pulls the gas in and internal energy attempts to push it out. This complex interplay suggests that dark matter is not just a static scaffold. Its distribution might be subtly influenced by the very baryons it controls. While dark matter is dominant, the gravitational pull of a large concentration of baryonic matter, like a massive galaxy forming at the center of a halo, could theoretically alter the distribution of the surrounding dark matter over time, pulling it slightly more toward the center in a process known as adiabatic contraction. Conversely, if feedback blows out a significant amount of gas, the gravitational potential of the halo becomes slightly shallower, potentially allowing the dark matter to expand outward a tiny amount. These back and forth effects are incredibly subtle and horribly difficult to model or observe, but they hint at a true dialogue between the visible and invisible components of the universe, a feedback loop operating on a scale and over a time frame that is almost impossible to comprehend. Unraveling this mysterious connection is arguably the next great frontier in understanding cosmic structure. We are moving from a model where dark matter is the sole architect to one where the intergalactic medium is an active participant, its behavior shaped by both the invisible hand of dark matter and the violent, energetic processes born from stars and black holes. This means that to truly map the dark universe, we must first completely understand the complex physics of the visible one. The behavior of the gas in the cosmic web is the only key we have to deciphering the nature of dark matter itself. Every detail we glean about the temperature, density, and distribution of the intergalactic medium doesn't just tell us about atoms. It places another constraint on the properties of the particles that make up the vast, invisible majority of our universe, slowly bringing the ghost out of the darkness and into the light of our understanding. Now consider a single beam of light from a distant quasar, a journey that can take over 12 billion years to reach our telescopes. Along that immense path, it doesn't encounter a single, uniform medium. Instead, it slices through a cosmic timeline. The photons that were absorbed by a cloud of hydrogen just a billion light years away from us are telling us about the state of the intergalactic medium a billion years ago. Meanwhile, the photons absorbed by a cloud 10 billion light years away carry a message from 10 billion years in the past. When we analyze the resulting spectrum with its forest of absorption lines, we are not looking at a snapshot. We are reading a historical scroll, a continuous record of the universe's evolution written along one incredibly narrow line through space. This is both the greatest gift and the most formidable challenge in studying the intergalactic medium. Every observation is a blend of countless different eras, all superimposed onto a single data set. This creates a fundamental deconvolution problem for astronomers. It's like trying to understand the history of a city by drilling a single, narrow core sample straight down through layers of dirt, concrete, and artifacts. You might find a layer of modern asphalt, then Victorian-era bricks, then ancient pottery shards, all in a single column. But you have no way of knowing if the Victorian layer extends for a block in every direction or if it's just a single, buried cobblestone path. Similarly, a dense cluster of absorption lines at a certain redshift in a quasar spectrum tells us that there was a lot of neutral hydrogen at that specific distance and time. But we cannot tell from that one spectrum whether this represents a vast, cosmic wall-like structure or a single, lucky dense cloud that just happened to lie directly in our line of sight. The light gives us a one-dimensional view of a three-dimensional universe and then further complicates it by adding the fourth dimension of time. To solve this four-dimensional puzzle, astronomers must rely on statistics and the power of multiple sightlines. This is the driving force behind massive sky surveys like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument. By collecting the spectra of not one, but hundreds of thousands of quasars spread across the sky, scientists can begin to assemble a true three-dimensional map. They can see if that dense cluster of absorption lines appears in the spectra of many quasars that are close to each other on the sky. If it does, they can triangulate its position and infer the true size and shape of the cosmic structure that caused it, effectively building a tomographic image of the ancient universe. This is how we map the cosmic web, not by seeing it directly, but by seeing the shadows it casts from thousands of different backlights and then computationally assembling those shadows into a coherent structure. Yet, even with this powerful approach, immense mysteries persist. The evolution revealed by these time-delayed observations is not always smooth or predictable. We can track how the density of the Lyman-alpha forest changes over billions of years, watching the universe become more transparent as reionization completes. We can see the overall temperature of the intergalactic medium rise and fall in response to the heating from the first quasars and the subsequent cooling from cosmic expansion. However, the details are often chaotic. Some lines of sight show evidence for a very rapid heating event at a certain time, while others from a similar era show a much more quiescent and cooler medium. This patchiness suggests that the universe's evolution was not a single, coordinated event, but a series of local transformations where your experience of cosmic history depended dramatically on your location. A region near an early quasar would have been ionized and heated billions of years before a quiet region in a deep void, and our singular viewpoint from Earth captures only a tiny fraction of this grand and variable narrative. The ultimate challenge lies in connecting these discrete points in time. We have excellent maps of the universe at redshift 0 from surveys of nearby galaxies. And we have increasingly detailed maps of the young universe at high redshifts from the Lyman-alpha forest. But the middle chapters of the story, the several billion years where galaxies matured, black holes grew to power, and the cosmic web took its modern form, are still blurry. It is incredibly difficult to track the same filament or the same void over time because we are seeing each one at only one moment in its existence. We must instead rely on simulations to interpolate, to show us how a structure seen at redshift 4 might evolve into what we see at redshift 2, and then again to what we see today. The discrepancies between these simulated evolutions and the actual, observed time slices provided by quasar spectra are the clues that guide us toward a deeper truth, highlighting the missing physics in our models and urging us to look closer, to gather more light, and to continue reading the universe's deepest history written in the delayed whispers of ancient light. Looking forward across timescales that dwarf human history, we arrive at the ultimate question of cosmic destiny. What becomes of the vast ocean between the galaxies over the unimaginable trillions of years to come? The fate of the intergalactic medium is not a simple story of gradual fading. It is a complex tug of war between the relentless force driving the universe apart and the subtle, persistent pull of gravity trying to hold it all together. A battle that will dictate the final state of all matter not bound within galaxies. The dominant force in this cosmic future is without a doubt the accelerated expansion driven by dark energy. As this mysterious repulsive force continues its work, the distances between galaxy clusters will grow at an ever-increasing rate. For the intergalactic medium, this means a future of profound isolation and dilution. The filaments of the cosmic web, already incredibly thin, will be stretched to the point of breaking. The gas within them will be pulled apart, its density plummeting towards zero. In this scenario, the universe doesn't just expand, it effectively evaporates. The warm-hot intergalactic medium will cool and thin to such an extent that it may no longer be detectable, even in principle. The constant rain of the cosmic ultraviolet background will fade as galaxies become too distant to see and their stars burn out, halting the constant reionization that has kept the hydrogen transparent for billions of years. In the utter cold and darkness of the far future, the IGM could become an almost perfect vacuum, a true void where the average density is little more than a single atom per cubic meter, a lonely and silent end for the medium that once birthed all structure. But this bleak, frozen fate is not the only possibility. Gravity, though it is losing the war on the largest scales, never truly surrenders. On more localized scales, its pull continues to work, and this suggests a more cyclical future for at least some of the intergalactic medium's material. Within the immense but finite bounds of a future supercluster, an island universe gravitationally bound against the general expansion, a slow, eternal dance of matter may continue. Gas that was once part of the cosmic web but remains within the supercluster's gravitational sphere of influence will continue to flow along the ghostly remnants of filaments, gradually falling toward the largest remaining structures. This material could provide a trickle of fuel for future generations of stars, a final reservoir for galactic renewal. This cycle, however, will be drastically slowed and altered by the changing conditions. The galaxies within these isolated superclusters will themselves be evolving. The largest will likely have grown into monstrous elliptical galaxies, having consumed all their smaller neighbors. Their supermassive black holes, having feasted during earlier eras, may now be quiescent. Without the violent feedback from quasars and starbursts to reheat it, the intergalactic medium within these island universes might gradually cool. Some theories even suggest that in these quiet, deep futures, the cooled gas could eventually collapse directly into monstrous, isolated dark matter halos, forming vast, planet-like objects made primarily of hydrogen-frozen relics in the darkness. The greatest mystery lies in the potential for entirely new, unknown physics to emerge over these incomprehensible timescales. The current fate of the universe is predicated on our understanding of dark energy as a constant force. But what if it isn't? Some models suggest dark energy could evolve, perhaps growing stronger and culminating in a big rip that tears apart all structures, including atoms themselves, leaving the IGM as a fragmented sea of fundamental particles. Conversely, it could weaken or even reverse, allowing gravity to eventually halt the expansion and begin a great contraction. In this scenario, the intergalactic medium would face a dramatically different fate, slowly heating once more as the universe collapses, eventually being compressed back into the hot, dense plasma from which it first emerged billions of years earlier, a perfect cosmic symmetry of beginning and end. Ultimately, the intergalactic medium's destiny is inextricably linked to the nature of the dark energy that now governs the cosmos. Its future is a choice between fading into irrelevance as the universe becomes a cold, empty void, or participating in a final, slow-motion cycle of matter within gravitationally bound islands, a last flicker of structure in an otherwise dark and expanding ocean. The answer depends on forces we have only just begun to detect, let alone understand, making the ultimate fate of the cosmic web one of the most profound and humbling mysteries of all. But for all our grand theories and sophisticated simulations, we are ultimately prisoners of our own technology. Every mystery of the intergalactic medium we've explored is in some way a reflection of our own observational limitations. We are like deep-sea explorers trying to map the ocean floor from a boat on the surface, using a narrow tube to glimpse a world we cannot fully enter. Our current tools are simply not up to the task of seeing the cosmic web directly, and this fundamental technological barrier is the source of much of the speculation and debate that defines this field. The heart of the problem lies in the very nature of the intergalactic medium. We are trying to observe something that is defined by its lack of substance. The gas in the cosmic web is so incredibly diffuse that its signal is unbelievably faint. Imagine trying to see the heat rising from a single, lit candle from a distance of 10 miles on a windy day. Now scale that impossibility up to a cosmic level. Our most powerful X-ray telescopes like Chandra and XMM Newton are heroic instruments, but they were designed for a different universe, one of bright point sources like black holes and neutron stars. They lack the sheer collecting area, the immense light bucket capability required to gather enough photons from the tenuous glow of the warm-hot intergalactic medium. It's like trying to fill a swimming pool with a water dropper. The process is so slow and inefficient that the signal is easily lost in the background noise of the universe. This challenge of detection is compounded by the issue of foreground contamination. Our view of the distant IGM is filtered through the crowded and complex environment of our own galactic neighborhood. The Milky Way's halo is filled with its own hot gas, which creates its own absorption and emission lines that can masquerade as the intergalactic signal we so desperately seek. Disentangling a faint, distant whisper from the loud, local conversation is a monumental task in statistical analysis and modeling, one where any small error can lead us to a false detection or cause us to miss a real one entirely. We are, in effect, trying to hear a distant, faint melody while standing next to a roaring jet engine. This is why we so often rely on indirect methods like the Lyman-alpha forest and the Sunyaev-Zeldovich effect. They are brilliant workarounds, allowing us to infer the presence and properties of the IGM by reading its effect on something else we can see clearly. But these are inherently limited techniques. A quasar spectrum gives us a core sample, a one-dimensional line through a three-dimensional structure. It tells us what's along that specific path, but it doesn't reveal the full shape, size, and connectivity of the cosmic filaments. It's like trying to map a forest by only examining the trees that fall directly on a single, straight path. You get detailed information about those specific trees, but you miss the grandeur of the entire ecosystem. The promise of a revolution, however, is on the horizon, embodied by a new generation of telescopes currently in the planning stages. Missions like the Lynx X-ray Observatory, a flagship concept proposed to NASA, and Athena, the advanced telescope for high-energy astrophysics, planned by the European Space Agency for launch in the 2030s, are not just incremental improvements. They are quantum leaps in capability. These observatories are being designed with one specific goal in mind: to see the unseeable. Their X-ray mirrors will have a collective surface area orders of magnitude larger than anything currently in orbit, transforming our water dropper into a fire hose. This immense collecting power will finally provide the sensitivity to detect the faint X-ray glow of the WHIM, not just in lucky, compressed regions near clusters, but throughout the filaments of the cosmic web. But it's not just about sensitivity, it's also about vision. These future telescopes will possess incredibly high-resolution spectrometers, Instead of seeing a single, blurry absorption line from highly ionized oxygen, we will see that line split into a detailed profile, revealing the gas's temperature, density, and velocity structure along the line of sight. This will allow us to do more than just confirm the WHIM existence. It will let us study its physics. We will be able to watch how gas falls onto filaments, how it is shock heated, and how it is eventually siphoned off to feed growing galaxies. We will move from simply knowing the gas is there to understanding how it behaves. The impact of this will be transformative. Directly imaging the cosmic web will solve the missing baryon problem definitively, allowing us to finally close the cosmic ledger and account for every atom. It will provide a critical test for our models of feedback, showing us exactly how energy from galaxies is deposited into the IGM and how efficiently it travels. It could even allow us to map the weak magnetic fields that thread the voids by seeing how they polarize the X-ray light. These telescopes won't just provide answers, they will open up entirely new lines of inquiry that we haven't even thought to ask yet. They are the keys to the next great era of cosmic discovery, promising to turn the faint, theoretical outlines of the cosmic web into a vivid, detailed map, finally bringing the universe's largest structure into clear view. Even with our most powerful supercomputers and our most sophisticated algorithms, we are still, in a very real sense, building digital universes that don't quite behave like the real one. This brings us to a deeply humbling frontier, the 29th mystery, the simulation discrepancies. For decades, cosmologists have been crafting incredibly detailed virtual cosmoses, governed by the laws of physics as we understand them, all in an effort to replicate the structure we observe. These simulations are monumental achievements, tracking the gravitational dance of billions of particles of dark matter and the complex hydrodynamics of the accompanying gas. They produce breathtaking visualizations of the cosmic web, with its elegant filaments and gaping voids that look strikingly similar to the maps we infer from galaxy surveys and quasar spectra. Yet, when we zoom in and ask precise, quantitative questions about the intergalactic medium within these digital worlds, the answers often don't match the data. The devil, as they say, is in the details, and these details are revealing critical gaps in our knowledge. One of the most persistent mismatches lies in the temperature of the gas. Our simulations tend to predict an intergalactic medium that is, on average, somewhat cooler and thermally quieter than what we actually measure from the Lyman-alpha forest. The real universe appears to be a more violent and turbulent place, with more pockets of superheated gas and a wider range of temperatures than our models can easily account for. This suggests that our simulations are underestimating the amount of energy being injected into the cosmic web. The usual suspects are the feedback processes from galaxies, supernova winds, and active galactic nuclei. It seems that in our digital universes, we either aren't putting enough energy into these events, or we aren't distributing it correctly. The energy might be too localized, blowing apart individual galaxies instead of gently heating the vast volumes of space between them. Or we might be missing entirely new sources of heating, perhaps from the decay of exotic particles or from turbulent energy transfer processes we haven't even conceived of yet. The problem extends to the very distribution of the gas itself. While simulations get the large-scale architecture of the cosmic web broadly right, they often struggle with the finer textural details. They tend to produce an IGM that is either too smooth or too clumpy. For instance, they might underproduce the number of very narrow, sharp absorption lines in the Lyman-alpha forest, which correspond to the smallest, densest, and coolest gas clouds. Conversely, they might overproduce the number of broader lines from hotter, more diffuse gas. This is a critical shortcoming because this texture isn't just cosmetic, it encodes the history of the gas. An abundance of small, cool clouds might tell us that our models of radiative cooling are too efficient, allowing gas to fragment too easily. A lack of them might mean we're missing the mechanisms, like magnetic confinement, that allow these delicate structures to survive in a hostile environment. Getting this wrong means we are misreading the story of how structure forms on the smallest scales. Perhaps the most significant discrepancy involves the pervasive pollution of the intergalactic medium with heavy elements. We know from observation that this enrichment is widespread, but our simulations have a notoriously difficult time replicating it. The challenge is one of scale and efficiency. In a typical simulation, when a supernova explodes, it dumps a colossal amount of energy into a very small volume of space. In the real universe, this energy might channel through hot bubbles in the interstellar medium and blow out in a relatively focused wind, carrying metals far into the halo. But in a simulation which can't possibly resolve these small-scale structures, the energy often has no choice but to explode violently in all directions. The result is either a feedback event that is too weak, failing to push the metals out of the galaxy, or one that is far too strong, completely shutting down star formation and blowing the gas out to distances that are unrealistic. The models struggle to find that perfect, balanced outcome where enriched gas is gently lifted and distributed across intergalactic space, which is exactly what the observational evidence tells us must happen. So where does the fault lie? Are these discrepancies telling us that our fundamental astrophysics is wrong, or are they simply exposing the unavoidable limitations of our computational methods? The answer is almost certainly a blend of both. On the technical side, we face the eternal problem of resolution. A simulation that models an entire universe cannot possibly also model the explosion of a single star. Cosmological simulations use a workaround called subgrid physics, where they use simplified recipes to approximate the effects of these small-scale events. We tell the simulation, if a galaxy has this many stars, then inject this much energy back into the gas. But these recipes are crude approximations. They contain adjustable parameters that are tuned or calibrated to make the final simulation look something like the real universe. This is a necessary fudge, but it means we might be getting the right answer for the wrong reasons, papering over our ignorance with a numerical fix. On the other hand, these persistent failures could be pointing to genuine, undiscovered physics. The discrepancies are like a chorus of voices from the cosmos, telling us our list of ingredients is incomplete. Perhaps magnetic fields, which are notoriously difficult to include in large-scale simulations, play a far greater role in confining gas and channeling outflows than we currently appreciate. Maybe the nature of dark matter isn't as simple as the cold and collisionless model we assume. If dark matter particles had even a tiny ability to interact with each other, it could subtly change the growth of the cosmic web skeleton, which in turn would alter how the gas flows into it. Or perhaps there are entirely new sources of energy or turbulence operating in the vast voids that our models don't account for. Each mismatch between simulation and observation is a potential clue, a signpost pointing toward a deeper layer of cosmic complexity we have yet to unravel. These digital universes are not just predictive tools, they are our most sophisticated testing grounds, and their failures are far more instructive than their successes, forcing us to question our assumptions and driving the next great revolution in our understanding. And so we arrive at our final mystery, a question that transcends pure astrophysics and ventures into the profound realm of philosophy. After exploring the violent feedback, the delicate structures, and the cosmic evolution of the intergalactic medium, we are left to ponder a possibility that is as unsettling as it is awe-inspiring. What if the specific properties of this vast, invisible ocean are not merely a random outcome of physical law, but a fundamental prerequisite for our own existence? This is the anthropic connection, the idea that the universe we observe possesses the properties it does because if it were any different, we would not be here to observe it. Consider the incredible precision required for galaxies like our Milky Way to form and thrive. The entire process is a cosmic tightrope walk, and the intergalactic medium provides the rope. Its density is a critical dial. If the average density of the IgM was significantly higher, the increased gravitational pull and the sheer abundance of gas would cause runaway collapse, forming far too many stars far too quickly. The result would be a universe dominated by massive, short-lived stars that explode in a frenzy of supernova, sterilizing any potential planets with relentless radiation long before complex life could ever emerge. Conversely, if the density were just a fraction lower, the gravitational tug would be too weak. Gas would never condense effectively into galaxies at all. The cosmic web would be a ghostly, ineffective skeleton, and the universe would remain a dark, starless expanse of isolated hydrogen and helium, a forever silent and unlit void. The IgM's density sits perfectly within this narrow Goldilocks zone, allowing for the steady, sustained galaxy growth that ultimately leads to stable solar systems and habitable planets. The temperature of the intergalactic medium is another finely tuned parameter. That pervasive heat from the cosmic ultraviolet background acts as a universal regulator. If it were too intense, it would prevent gas from cooling anywhere, effectively shutting down star formation across the entire cosmos. No new stars would mean no new heavy elements and no new planets. But if this background radiation were too weak, the opposite problem would occur. Without that constant, gentle heating, gas in the vast reservoirs of the cosmic web would cool too efficiently. Galaxies would gorge themselves on this cold fuel, triggering ferocious, uncontrolled bursts of star formation that would quickly exhaust their gas supplies and leave behind galactic wastelands. The IgM's specific temperature profile creates a balancing act, allowing gas to cool gradually and feed galaxies at a sustainable rate, fostering the long, stable lives necessary for biological evolution. Even the IgM's ionization state is crucial. A fully neutral universe would be opaque, shrouding all distant light in a fog of hydrogen and preventing us from ever learning about the cosmos's history and laws. A partially ionized medium would create a chaotic and unpredictable environment for light to travel. The fact that the IgM is a highly ionized plasma is what grants our telescopes a clear view across billions of light years. This transparency is not just convenient for astronomers, it may be essential for life itself on certain worlds. The reionization process, driven by the first stars and galaxies, flooded the universe with ultraviolet radiation that could have sterilized any nascent life on unprotected planets. The timing and patchiness of this event were therefore critical. Had it happened too early or too uniformly, it might have wiped the slate clean across the entire cosmos. The specific history of our IgM allowed for safe pockets where life could later arise and eventually inherit a transparent universe ready for exploration. So, how do we interpret this apparent fine-tuning? One perspective is to dismiss it as a staggering but ultimately meaningless coincidence. In an infinite multiverse, every possible combination of physical constants and initial conditions exists in some separate universe. We simply find ourselves in one of the rare universes where the numbers are just right for life to emerge, and we shouldn't be surprised to observe conditions that allow our existence. This is the anthropic principle in its weakest form, a statistical selection effect that requires no deeper explanation. Yet others see this not as a coincidence but as a profound clue. The precise calibration of the intergalactic medium's properties could point toward a deeper level of physical law that we have not yet uncovered, one where the constants of nature are not arbitrary, but are necessarily linked in a way that inevitably leads to complexity and consciousness. Perhaps the laws of physics are not just a random set of rules, but are somehow optimized for the emergence of life, with the IgM playing a central, orchestrating role in that cosmic destiny. This is not necessarily a call for a divine architect, but rather an openness to the idea that our universe is strangely bio-friendly, and that this friendliness demands an explanation beyond brute chance. Ultimately, the intergalactic medium is more than just the space between galaxies. It is the foundational environment, the cosmic womb from which galaxies are born, and the regulatory system that governs their lives. Its specific properties appear to be exquisitely fine-tuned to allow for a universe that is both structured and livable. Whether this tuning is a fortunate accident in a vast multiverse or a signpost to a deeper truth about reality is perhaps the greatest mystery of all. It leaves us with a humbling thought. The emptiness of space is not empty at all. It is a carefully arranged setting, and we are part of the story it tells. From the ghostly hunt for missing matter to the searing enigma of the warm-hot intergalactic medium, from the magnetic fields woven through nothingness to the delicate cool clouds that defy evaporation, the space between galaxies is anything but empty. It is a dynamic, chaotic, and profoundly mysterious ocean, governing the birth and death of galaxies, recording the universe's history, and challenging our very understanding of physics. We've journeyed through 30 of its deepest puzzles, each one a doorway to a larger truth about the cosmos, and each one revealing how much we have yet to learn. Unraveling these secrets will demand nothing less than a new era of cosmic exploration. It calls for next-generation telescopes like Athena and the upcoming giant observatories, instruments with the sheer power to finally capture the faint whispers of the cosmic web and map its invisible architecture. It requires supercomputers of unprecedented capability, running simulations so detailed they can finally model the violent dance of feedback and the subtle influence of dark matter. And perhaps most thrillingly, it may necessitate a revolution in physics itself, compelling us to look beyond our standard models to explain the origin of cosmic magnetism, the nature of dark matter, and the bizarre fine-tuning that allows our universe to exist. This isn't the end of a story, but the beginning of a far grander one. The greatest discoveries about the intergalactic medium are still ahead of us, waiting for the tools and the minds brave enough to seek them out. So we want to hear from you. Which of these cosmic enigmas captures your imagination the most? Is it the missing baryons, the phantom touch of magnetic fields, or the violent feedback that shapes galaxies? Let us know your thoughts in the comments below. And if you're hungry for more journeys to the edge of understanding, make sure to subscribe and hit the bell for our next deep dive into the universe's most captivating